Okay, so I'm going to record it from here on out for everyone who either like to watch it later or who can't make it now or might want to revisit it later. I also just sent out to the on that department email that I had a little bit earlier the slides for this. So in case you want to go back a little earlier or go a little bit forward or a little bit back as I'm going through the lecture slides on your own, you can certainly do that. For my particular class, which is only 3 students, that's up on Sakai, so you can see it on Sakai as well. The code is also up on Sakai. If you're not in the class, but you're interested in seeing the code, or I mean, I'll show it you. We'll go through the code on the screen during the class, but for those of you who might want to take a look at it later, let me know. I can send it to you. Those files aren't nearly as big as the video file will be. It'll be much easier to just send that over email. But that's but with that, I think we'll get started here. The only thing I wanted to note is for the class itself, there is a problem set that was due today on projection methods. So just make sure you email that to me sometime by the end of the day today. That's the last one. And then you have your final projects that you know that you're going to be working on. We've already talked about them. So those will be due during the final exam slot. And so you know what you got to do for those. We talked about them a little bit. I'll make sure that by the end of the week I send you a little bit more formal discussion of what all we talked about and what all is expected, so that you'll have that. But I think it's pretty clear. It's pretty clear for both of you then. Okay. Well, without further ado, we're going to go ahead and get started here. Welcome everybody. I'm looking forward to going through this lecture with everybody. And this is something I consider a little bit more exploratory, both on my part. So how I'm kind of viewing this is, one thing I like to do with the methods course, and I've done this ever since I started teaching it, is I usually like to, toward the end, try to find one of the most powerful algorithms that I can, and then go through that algorithm with the students. And for the past couple of years, that's been the Smolyak algorithm. And I usually want to, I do it toward the end so that, you know, as the students are moving into their 3rd year and into the dissertation stage, they're not hindered by computational roadblocks any more than anyone else would be hindered by computational roadblocks. That they kind of have available to them sort of the best of the best. At least they have a basic understanding of what the best of the best looks like. So I've tried to do that every year in this class. And it got to the point where I've been talking to people over the past, couple of years from different departments, different conferences and things about what's been going on and what they're using and how they're solving different things. And machine learning has started to crop up a little bit, a little bit here, a little bit there. Some empirical people are using it, a few structural people are starting to use it. And I wanted to look into it for this class, and also for myself to see if it's something that, could be of interest to me. Turns out it is very much of interest to me for a lot of reasons I'll go into. I think it's probably very much of interest to a lot of you for a lot of reasons I'll go into. That's sort of how this started, with me trying to find, me talking to people, realizing that the Smolyak algorithm is probably not the best of the best anymore. In fact, at this point, I can say the machine learning is quite a bit easier and probably quite a bit more powerful than the Smolyak algorithm. And it's pretty easy to get it off the ground, actually. And that's probably one of my favorite parts about it. At least there's several different algorithms, so I won't be able to go into all the algorithms. But I'll go pretty deep into one particular algorithm, and then I'll kind of talk a little bit about some of the other algorithms that people have been using and the basic idea behind them, and sort of what I think unites all these different algorithms under the umbrella of machine learning. But nevertheless, I think it probably will be where the profession is going. I think you'll probably see it more and more because it is fairly easy to implement and because it is incredibly powerful. People have been using these sorts of algorithms in industry for a long time now. In fact, the algorithm that I'm basing the algorithm that I'm going to show you today, the one that's going to take up the most time, was in a recent paper just a couple of years ago. But it's based on machine learning methods from a textbook in 2005, I think. So in the computer science community, machine learning was already pretty well established back then. I'll sort of talk about why I think it didn't really make it into mainstream economics until a lot later. But it's not necessarily new ideas. The algorithms aren't necessarily new, but economists are just starting to adapt them pretty recently. So if at any point anyone has any questions, or if something with Zoom is up and we have issues, feel free to let me know. But I think we'll go ahead and get started then if everybody is ready to go. I'll say right now, I don't know exactly how long this will take. I mean, the class lasts 3 hours. I'm hoping, I tried to write it up such that it takes roughly 3 hours. But I've never taught this particular lecture before. This is sort of new for me and for everybody. So it might run a little bit early, might run a little bit late, depending on how exactly it goes, but I will try my hardest to keep it in 3 hours, but I'll be able to time it better, I think, in future iterations of this course, and I'm going to be able to time it here. So, all right. Any questions from anybody before we get started? Okay. So I'll talk about machine learning a little bit. And I've got some code here, so you'll be able to see some code that we're going to go through and the slides. I'll alternate back and forth between them. And let me know, certainly, if you can't see them for whatever reason. So machine learning methods. This is what we're going to be going over today. I started to get interested in this, like I said, talking to people at conferences. Some economists have started to use it, but I also have my brother-in-law founded a tech company down in Indianapolis. And his company, he's very much plugged into the venture capital community and very much plugged into the tech industry in general. So he knows people at Facebook and Google and all these different places. And so I like to talk to him about this stuff, or Thanksgiving and Christmas and get-togethers and things like that. And I've asked him recently about machine learning. And so he was telling me about the power of it, but even he, who's kind of plugged into the tech world, didn't really understand it completely. And so a lot of people know that it's something that's very commonly used, something that's very powerful. He's thought about hiring people at his company to do it, but he didn't know very much. He referred me to a couple of experts who knew a little bit more, but there's still, it's sort of a fuzzy term. You'll see why it's sort of a fuzzy term, and there's reasons why it's sort of a fuzzy term, is because it's actually kind of a lot of different things at once. There's actually a lot of algorithms that fall under this category of machine learning, and I've never actually found one good definition from someone else as to what I think all those algorithms have in common. I'm going to propose my own, which seems to be, to me, what sort of unites them all. But I haven't actually been able to find a concrete definition of machine learning besides basic things like, well, it's like thinking like operations done by a computer. That's kind of what everyone tells me. This sort of pattern recognition, identifying and categorizing images, this sort of thing, detecting spam and incoming email messages. When you're typing something into Google, right, and it starts to autofill for you, these are all machine learning algorithms that are being implemented to try to forecast what you're going to say next, or what you're thinking about doing next. All of the algorithms that are doing this are types of machine learning algorithms, and they're really powerful. They've gathered a lot of attention in big tech and private industries. I mean, companies like Google, Facebook, Apple, Amazon, they've made billions of dollars by implementing these algorithms. That's really what the heart of Google's business model is just a class of really powerful, very well-trained machine learning algorithms. The most common one they like to use is neural networks. That's something my brother-in-law told me, that Google is all about neural networks. So Google Maps is a neural network. And they're constantly updating and sort of expanding that neural network. And we'll talk a little bit about what neural networks are. Some economists are using neural networks as well. And the idea behind them is not actually that complicated. But they work really well. They've made a lot of people a lot of money, and they've provided lots of consumer surplus to everyone who's, you know, been using Google or anything on the internet or Google Maps or any of the services that rely on these algorithms. You know, a big increase in welfare, I think, has resulted from a lot of that. But academics have been kind of slow to get on the train. Like I said, a lot of these algorithms have been around for a while. You know, Google was implementing this stuff at least in the 2000s, possibly in the late 90s. I don't know exactly what they were using in the early iterations of their search engine, for instance. But it's been around for a long time. If I were to take a guess as to why I think academics and economists haven't really jumped on board as much, I think it's probably because there's very little we understand about it. I remember going to a conference a few years ago, and Lars Hansen was at the conference. And there were a couple papers in that conference that used machine learning methods. They were very empirical papers. I think they were looking at trying to predict mortgage defaults or something like that using machine learning techniques. And Lars Hansen was sitting there in the front, and he was taking it all in. And they sort of asked him afterwards, you know, what do you think about this? How does it seem promising to you? And he could not get on board. He was very critical of it because there's very little about it that you can understand. It has very powerful predictive power, but a lot of the predictions in most cases, you can't really form standard errors around it. You can't really talk about limiting distributions. You know, the predictions work pretty well, it seems. They seem to be pretty accurate, but there's very little theoretical knowledge of how accurate they actually are. You know, why are they so accurate? Very little of this is understood. My understanding is, as more academics find this stuff really interesting and are getting into it, some of this stuff is starting to get proven. Techniques are being developed to start to do this sort of analysis on top of it. The tech guys never really cared about it so much. They basically said, it works, we plug it in, we can make money off of it. I don't remember if it was someone at Facebook or Twitter or something. Maybe it was one of these tech companies. They asked him, you know, some guy got a particular advertisement on his Facebook, and they said, well, why did this guy get his particular advertisement? He said, I don't know, our algorithm says he does. Well, how do you know? Like, what aspects of his profile and all his purchases and everything told him that he should get that advertisement? I have no idea. They don't know, right? They just plug in, it's like a big black box, and it works really well, and it makes them money. But they don't really understand how it works. Not necessarily how it works, but they don't understand the logic behind how well it works. They can't say anything really statistically sophisticated about the predictions that it's giving. And I think that's given economists and academics in general a little bit more pause coming to this, because we're not necessarily interested in getting the best possible forecast, right? And I think this is sort of a point that Lars Hansen made. We're much more interested in understanding why the predictions are the way they are. That's why we're academics, right? That sort of analysis is really crucial to academics in a way that, you know, it might not be for an industry guy who can make money off it in the next 6 months, even though he doesn't understand it. So I think that's maybe why it's been more slowly adopted by academics, because there's still a lot that's unknown about it. And as I mentioned, there's been some techniques that have been developed to try to do this sort of analysis. Like I think Stephanie Stancheva, who was it? We had someone last semester come and give a talk on machine learning using credit score data, trying to incorporate a neural network to do credit score data. And they were developing some techniques for doing some sort of input-output level analysis that weren't quite standard errors or confidence bands, but we're sort of getting in that ballpark, trying to understand what it was that was driving the predictions from, say, the raw input space. So some of these techniques are being developed currently, but they're sort of following the wave of private sector implementation. And so I think that's sort of where we are. But we're getting to the point where I think it's easy enough to do it and it's useful enough to do it that we don't need to worry about this stuff as much. It's also going to be, we don't need to worry about this stuff in structural methods as much. So this sort of talk is going to be mostly geared toward people who are doing structural work, who want to use this for structural work. You could also use it for, you can use a lot of these ideas for more empirical work too. I mean, a lot of the neural network stuff, some of this Gaussian process regression stuff will go over, you know, you could use all of these in empirical settings. And many people have very much reduced form settings, you know, very large enormous data sets with high dimensionality. This is sort of where you think there might be a lot of really nonlinear interactions going on. This is really going to be the toolkit you're gonna want to grab when you do that. And for that, you know, you might be a little bit more worried because it's going to be harder to draw these sorts of bounds. There's going to be less analysis that you can do relative to, say, more conventional frameworks. But for structural methods, it really doesn't matter that much, in the sense that, you know, the proof is in the pudding with the structural methods. What you're basically trying to do when you're trying to use these to solve some sort of functional equation, say you want to find an investment function in a large-scale DSG model, you know, if you can find that investment function and you can find that the Euler equation errors are very small, you know, it doesn't matter how you got there. And this is something I've been telling my students this whole semester. I like to liken it to, you know, as long as you come up with something that works, right? No one's going to ask you how you got there, right? No one. I like to liken it to there's a scene in the first Rocky movie where Rocky is basically, before he becomes a professional boxer, he's essentially a what would you call it, like a henchman for a loan shark, right? And so there's people who owe him money, who owe the loan shark money, and he basically goes and roughs them up till they pay, right? So they say he's going to go down to the dock and break their thumbs if they don't pay, guys who work at the dock or something. And so, you know, I always say, you know, no one has to know what goes down at the dock, right? You just go down to the dock and come back with a model that brings back small errors, and no one cares how you got there, right? That's kind of how it can be in methods, you know. So if you have something really convoluted, you know, it might not be pretty, it mimight not work as well, but, you know, if you've got something that works and it delivers accurate policy functions, doesn't really matter how you got there. You know, you go down to the dock and you get it done, and no one has to know what happened down there, right? So that's why I think machine learning is especially very good for structural methods, because we don't necessarily know what's happening down there at the docks. There's probably some thumbs getting broken, but, you know, it's coming back with something that is working pretty well. Right. So I think it's particularly fitting for structural methods, but because we don't necessarily care as much about that sort of thing. But the more empirically oriented folks can certainly use it as well, at least to make predictions, even if the analysis maybe isn't all the way where it might be for more classical sort of regression algorithms. So there's two basic kinds of machine learning that I've been able to gather. Really only one of them seems like the sort of thing that economists would be interested in, although there might be some use for the other one as well that I haven't thought of or don't know much about. But there's supervised machine learning and unsupervised machine learning. Supervised machine learning basically says you have a bunch of input data, and you have some output points that you know correspond to that particular output data. So you basically have a function, right? You have a domain, some points from the domain, and you have some points from the range. And you want to find out what the function is. It's basically a functional approximation, right? But you know that there's way more points out. There's the function has a much larger domain than the input data that you have. You have very few what they call training points or input points relative to all the different combinations that could be entered. So it really is sort of a functional interpolation exercise. You have a few points and you want to sort of generalize and interpolate or maybe extrapolate to a much broader set of points. Unsupervised machine learning, I haven't really seen any economists use it. I might be missing papers where they use it, but there's essentially it's not really functional analysis. Essentially, there is no range. So you might have a bunch of collection of data, but you don't really know what you want from it, right? So what it's usually used for is something like identifying patterns or categorizing things. So one thing you might do is you might have a set of images, you know, 10 or 15 images, and you basically give it to the algorithm and you say, look, I want you to find commonalities between these images and group them by common elements, right? But I don't necessarily know what I'm looking for here. Just kind of find some patterns for me, right? And that's referred to as unsupervised machine learning. So it's trying to kind of infer some of these natural structures that are present in the input data. So this can be used in pattern recognition, clustering, that sort of thing. Most of what I've seen the economists use is the supervised, because we're sort of a lot more interested in the functional approximations. But there may be use for the unsupervised out there. I haven't seen it yet. They've used it in industry, but it's not something that I've seen really been used in academia yet. But again, I'm an amateur at this, right? I've really only been coming at this stuff for the past few months or so. So as I said, I'm seeing this lecture as more of us exploring some of this stuff together along the dimensions that I have found it to be most useful. But I'm not going to sit here and claim to be an expert at machine learning, because I'm certainly not. I found a few powerful and useful algorithms that I kind of wanted to share with everybody. But there's probably going to be a lot of questions you may have that I'm not going to have answers for, because I'm very much an amateur at this, just like many of you are. All right, we're going to focus for this lecture. I'm going to focus entirely on the supervised kind, because that is the kind that seems to be most relevant for most economists. So what is that, supervised machine learning? Well, it's really not that different from what economists are trying to do all the time, which is why I think economists could really use a lot of these techniques. Essentially what you're doing here is you're trying to approximate a solution to a functional equation, right? So maybe if you're in, solving some sort of a structural model, you've got some sort of consumption policy function you want to solve for that's all endogenous. And you have some Euler equation, some resource constraint, maybe some other things. Maybe you have some sort of, Taylor rule if you have a monetary policy, an economy with monetary policy. You have a bunch of other stuff, and you want to sort of find what the consumption policy function looks like. Basically, that consumption policy function takes you from a domain, a bunch of different states, all the different states that govern the economy, and then it gives you some output. It tells you what the level of consumption is, and that's going to have to meet market clearing conditions and optimality conditions, resource constraint, all that sort of stuff, has to all sort of clear simultaneously, and that's a difficult thing to solve for, right? And that's essentially what we're doing with structural methods, is solving for things like that. But those are who are more empirically oriented, who are maybe just interested in this more reduced form stuff. Maybe you have some sort of complex nonlinear regression, and essentially what you're finding there is some sort of conditional expectation function, right? That's what you're interested in. You want to be able to predict the conditional expectation of a given, dependent regressor based on all the independent regressors. And so you can use it in that context as well. In both cases, we're sort of after the same thing, which is some sort of approximate solution to a functional equation, right? It's really not that different than what we've been doing all semester in this class, which is basically solving this sort of stuff, or what a lot of econometricians are trying to do. The key difference that I see between machine learning and some of these other, say, more classical methods, projection methods or dynamic programming methods, or some of these other methods that are employed a lot by folks of a more structural bent and folks of a more reduced form bent, the scope is way larger for machine learning. The domain space is much, much bigger. You might have hundreds or thousands of dimensions in the input space, and it's really capable of really extreme nonlinearities, all sorts of very crazy high order interactions between terms.
Hey, Zach, can I ask you something?
Yes.
Is your sense that this is really almost a free lunch, other than us updating our human capital, or do you see that these more traditional methods have particular strength as well that machine learning just won't give you?
I think
so it's an addition to our toolbox rather than a replacement of our toolbox.
I think it depends on how comfortable you are accepting things that you don't fully understand. I think so. A nice comparison, and I'm going to make this throughout the lecture. Machine learning can be interpreted as a type of projection method.
Sure.
And that it's you're basically going to try to approximate the function of interest with a collection of some sort of simpler basis functions.
Right.
And if you were to compare the sort of classical projection methods that we're aware of, you'd be thinking of something like Chebyshev polynomials, right? Use a sort of a Chebyshev collocation method. Now, machine learning is much more powerful than Chebyshev collocation. And I'll kind of explain kind of how that is, and you'll sort of see it in practice. But what you get with Chebyshev collocation that you don't get with machine learning is you have lots of theoretical results that are very well established, right? So there's the Chebyshev truncation theorem, which actually pins down the degree of accuracy of your approximation based on the values of the coefficients that you arrive at, right? So with some of these more classical methods, I think economists have felt more comfortable with them because we can kind of theoretically understand why they work and the conditions under which they work. And my understanding is with machine learning, we don't have the sorts of theorems like that,
okay,
right? So I do think in a sense, it's it will supplant those sort of methods. If you just want something that all you care about is the solution, then I think it's probably something that's more of a substitute than a complement.
Okay.
It's going to be something that's more likely to replace existing methods than to complement them. But if you're more like a Lars Hansen type and you care a lot about understanding what's going on, then I think you would probably stick with the more classical methods. I think the difference between them, as I've been able to gather, is really the amount we understand about how they work and why they work. But in terms of the raw power, I really don't think there's any comparison. I think the machine learning outperforms the classical methods hands down in all the cases that I've been able to find.
Thank you.
So, yeah, so that's my understanding of it. Again, coming at this as an amateur, so that with all the with the little experience that I have, that seems to be sort of the trade-off that you face, is how much do you care about understanding it. But essentially, so machine learning, we're thinking about supervised machine learning. We're thinking about sort of high order, large domain input space, hundreds of thousands of dimensions. A good example of this is image recognition. A lot of machine learning algorithms are used to recognize images, right? So you think about this, you think about sort of solving like a consumption policy function in a DSGE model. You're basically looking for a function that takes you from the relevant state to the economy. So maybe, some level of capital, some level of productivity, maybe some level of foreign asset holdings, maybe some price level or some level of inflation or whatever it might be, whatever whatever you would consider the state of the economy for your particular model. And then you're going to map that into something of interest, say a consumption function, an investment function, monetary policy rule, whatever it might be. Well, with image recognition, it's not so different in a sense that basically each pixel in the image is basically a state. It's a dimension, and it could vary across the color spectrum. And there's a whole bunch of these. There's thousands or millions of them. And but essentially, it's doing the same thing. It's trying to answer some question about the underlying input space that you've given it. So it's a very high dimensional problem, even if it's something pretty simple. So like, here's a good example. This is a machine learning algorithm that's kind of designed for image recognition. Is this a picture of Sylvester Stallone? Yes or no? In this case, it is. For anyone who's seen Rocky would know that this is a picture of Sylvester Stallone, right? But essentially what it's doing is it's got a massive input space. Omega would be our high dimensional pixel space here. And it's basically mapping this omega through a very complicated, highly nonlinear function into just a binary function, 0, 1, yes or no. Is this the person I'm looking for or not, right? We could take these sorts of methods and use them in economics, right, to answer the sort of questions you might be interested in, right? We might think about F as something like a consumption policy function, or we might think about it as, the conditional expectation in a highly nonlinear empirical reduced form regression, right? And so that's the basic idea of what we're going to be trying to do here, and then sort of how machine learning has been used in the past. But something like this, just to kind of go back to Rudy's question, if you were to try to use Chebyshev polynomials to answer this question, which you could, you could basically take Chebyshev polynomials, run it through like a logit regression at the end to try to get a 0, 1 output. Technically you could do that, right? You could basically use a Chebyshev approximation for all of these for all these different pixels, and the theorems would work, the theorems would hold, technically you would get an answer out of it. But it would probably take you, let's just say it would probably take more computing power than we have in the universe to do a simple problem like this. And for reasons I'm going to talk about, if you're going to use some of these classical methods, you could never really use these classical methods to handle problems like this. There's just the amount of dimensions that spiral out of control, and the amount of things you have to take care of, just grows out of control very quickly. And that gets to sort of my point, which is what I think most machine learning algorithms really are, and what I sort of consider my definition of machine learning to be. Machine learning seems to be an umbrella term for a collection of functional approximation algorithms that break the cursive dimensionality, right? So for those of you that are familiar with the cursive dimensionality, it's basically this idea, right, that as you increase the input space, or the dimensionality of, say, your state space linearly, computation time and memory required grows exponentially, right? So if I have, 1 dimension and I have 10 grid points along that dimension, I add a second dimension. So now, say I have maybe capital, and now I want to have capital and productivity. If I have 10 grid points along each, I go from 10 to 100. And then if I want to have another dimension, I go from 100 to 1,000, right? and then I go from 1,000 to 10,000, and it grows exponentially. Sorry, even though I'm adding my inputs linearly, everything's growing exponentially. The thing that I found about all machine learning algorithms that I find is that they don't suffer from this curse of dimensionality for some reason, whether that be neural networks, Gaussian process regression analysis, random forest tree models. They all have the feature that basically, as you increase the dimensionality of the input space, computational time and required memory grow only linearly. So they grow at the same rate as the dimension size, which still boggles my mind. I've never actually had someone answer me clearly why this is. I don't know if anyone really understands fully why that is. But basically, all of the machine learning methods that I've seen have this property. That basically, if you want to increase the dimensionality of the state space, you only have to worry about increasing computational time and memory linearly, as opposed to the usual way, which is exponential. So that's really what I think defines machine learning. Every machine learning algorithm that I found has that feature. And it seems to be what lends that so much power, right? So if we go back to the Sylvester Stallone example, right? You know, there are thousands of pixels in there potentially. But, you know, you can handle that if your computational time and required memory increases linearly with the number of dimensions. It's still a lot of dimensions. It's still, you know, several thousand dimensional problem, but it's not, you know, a quadrillion dimensional problem, which it would be with classical methods, which is sort of what brings the sorts of problems that we have in machine learning, the pattern recognition, this sort of stuff, the sort of stuff that really would be completely impossible with classical methods, into the realm of feasibility with machine learning. It's this idea that it can actually break the curse of dimensionality. And again, why is that? I don't know. I really don't. I don't think anyone has a good sense of that yet. I think that's why people like Lars Hansen have been so reluctant to get on this train, because no one really understands why this works so well. Because the curse of dimensionality makes sense, right? From the time, you know, I got kids at, you know, the preschool age, and we have all these little, you know, beads and things that they use to learn math on, right? And back from the time we're in preschool, you've got the beads. It's like, well, I've got, you know, a single bead, and then I have 10 beads, and then I open that up to a square with, you know, 100 beads, and then I build up the cube for 1,000 beads, right? That's the curse of dimensionality. That's something we understand even from a very young age, right? The basic idea that as you scale inputs up linearly, the dimensions linearly, things are going to grow exponentially. So why exactly it breaks that, I have no idea. I really don't. If I were to take a guess, which would be a complete guess, just for the algorithm we're doing today, I think it has something to do with the power of optimal Bayesian updating, and maybe that generalizes to other classes of algorithms as well. But it's a complete guess. I really don't understand why, and I haven't been able to talk to anyone who can explain to me why that is. But be that as it may, it does work. I mean, it's the reason why Google exists, basically. It's the reason why Google is one of the largest companies in the world, Alphabet. It's the reason why all these tech companies have grown to tremendous heights, why they've been able to provide the sort of services that we've seen over the past, say, 20 years or so. It's basically all because of this, right? Because of this fundamental idea that the curse of dimensionality is broken for this class of algorithms. And we may not fully understand why, but we can go ahead and use it. So I think economists have been slow to do it, partly for that reason, because it's esoteric to understand. But the potential really is absolutely tremendous. So just to give you, you know, some examples, some papers. There've been papers out there that can predict mortgage loan defaults better than existing methods using machine learning techniques. There we go, Stefania Albanese. That was who we had out last semester to talk about the FICO scores. It wasn't Stenchek, it was Albanese. That you can predict consumer default better with FICO scores using the same exact data, because you can capture a lot of these high order interactions that the traditional methods can't capture. My old advisor, Jesus, has a recent paper just last year where he basically uses a neural network and he sort of solves a heterogeneous agent model like a Crucell-Smith type model without using shortcuts. Normally, Crucell-Smith kind of had this big approximate equilibrium where they kind of make a big shortcut that apparently Ed Prescott hated when he first saw it. but basically with machine learning, you can handle some of these heterogeneous agents models without really taking the shortcuts, right? I mean, you're still going to be using a discrete sort of approximation where something might be continuous, but you might be able to handle, you know, a distribution with, you know, that's encompassed by, say, dozens or even hundreds of states, and kind of actually keep track of that very carefully over time. That sort of becomes possible with machine learning. So you don't necessarily need to take some of these Grusel-Smith type approximations. You can actually just solve the raw heterogeneous agents model as it was. So so there's really tremendous potential here. It's a very powerful, once you understand how much the curse of dimensionality gets in your way, you'll realize the sorts of freedoms you'll have once you can actually break it. So what I'm going to focus on in this lecture, I'm going to talk about how you could use it to solve kind of bread and butter DSGE type models, the sort of structural models that we're usually interested in macro, that we've kind of focused on in this course. That's really what I'm gonna focus on here. I'm gonna follow an algorithm that was proposed by Scheidegger and Bilionis in a recent paper in 2017. It's actually interesting. I've been talking to Scheidegger about this. I've been in contact with him throughout the semester trying to understand some of this stuff. He has a recent paper in Econometrica, using an adaptive sparse grid method to try to solve kind of high dimensional DSGE problems like this. And so he's a smart guy, and he's, you know, very quantitatively sophisticated. But this paper was not published in Econometrica. It was published in some computation. It wasn't even computational economics. It was some, I can't remember what journal it is, but it's not a super high ranked journal. But if you actually look in the paper, I think the reason for that, I didn't actually ask him myself, but I think the reason for that is he actually mentions in the machine learning paper that it's a more powerful algorithm than his Econometrica paper. So he actually mentions that, you know, there's drawbacks from the Econometrica paper that are not here for the machine learning paper. And I think the reason why I didn't publish as well is probably for the reason I was talking about, because in the Econometrica paper, it was full of proofs. There was all sorts of theorems he could say about how well it converged and how well it performed. In the machine learning paper, there's none of that. Right? So they don't understand why it works so well, right? They can't prove why it works. They can't, you know, give conditions under which it works, right? But it just usually works, right? And I think that was it was probably a turnoff for a lot of the referees and a lot of us economists in the publication process who like to really understand why it works. So that's why even a less powerful algorithm might hit it somewhere like Econometrica if you can prove something about it. Whereas this algorithm is actually significantly more powerful from my understanding, but there's just very little we can say about it. So what he's proposing in the machine learning paper, though, is a machine learning algorithm known as Gaussian process regression. And I'll talk about specifically what Gaussian process regression is and how you'll do it, but it's not very hard to do, actually. And they basically propose a combination of Gaussian process regression, another high dimensional algorithm that you can use that's useful to combine with it for really large problems called active subspace analysis, and basically combining this with dynamic programming. So one of the things I really liked about this paper is most of it is basically just a straight value function iteration. There's not a whole lot involved in the implementation of it. If you can do a VFI, which most of us can, you're probably going to be able to do this no problem. So it's very powerful, but it's also very simple. That's one thing I like about it. It's a lot simpler than the neural networks stuff. So the neural networks is still pretty simple, but it's a little bit more involved to get off the ground. So this was one that I really liked because I think it's very accessible to a lot of people. Using this technique, they show that they can easily globally solve a DSGE model of 500 dimensions globally. So you can compare that with the closest competitor is a Smoljak algorithm, which is what I've normally been teaching for the past few years. And that algorithm maximizes around 20 dimensions when it's pushed really hard. Dirk Kruger has a paper where they kind of have an overlapping generations model with a bunch of different states. I don't remember exactly what they're trying to do with that, but there's basically 20 relevant states. And they solve it globally using Smoljak, which Smoljak is basically the best that sort of the classical algorithms have to offer. It's a variant of projection methods. So it uses Chebyshev polynomials to approximate the underlying solution. And you can get to about 20 if you're really pushing it really hard. You have some really, a ton of machinery, you have a lot of hardware, you can parallelize a thing, that's about the sort of classical max, right? And it's really clear in the machine learning paper that they're trying to beat this. Like 20 is, if you read the paper, like 20 is their threshold. They're like, we want to be able to solve things bigger than 20, right? I actually don't think that, one of my criticisms of the paper is I think it's way more useful. I think they're trying so hard to beat Smolyak that they're not seeing how the benefits that it has for things that Smolyak can do already, but that it's just way better at. So, something that maybe doesn't have 20 dimensions, something that maybe only has 5 dimensions. I mean, implementing a Smolyak algorithm for 5 dimensions is a nightmare, right? You can do it, it works, but it takes a lot of time. It's really finicky. It doesn't work that, there's, small adjustments might throw it off. But I'll show you here. What we're going to do in this class, I'm going to have a 5-dimensional DSGE model with a 4-dimensional control space, so like a pretty big maximization. And you'll sit there and watch it converge in a few minutes, which if you were to use classical methods, that could easily take days or even weeks to do that. And it's going to look very familiar to you. So I really think that where this algorithm has a lot of promise is not in the huge dimensions that the paper tries to sell you on. It's like, well, you can have a 500-dimensional model. Like, look, in structural work, nobody wants a 500-dimensional model, right? You can't understand what's going on in a 500-dimensional model. That's way too many dimensions, right? It's much better to have a concise model with 4 or 5 dimensions that you can really grasp and understand, but maybe have a lot of interesting nonlinearities, and to be able to solve that quickly, and to do it well and without having to put in a lot of extra effort to do that. That's really where I see the most power from something like this, is maybe you want to have, not a crazy dimension, not a crazy dimensionality in your state space, but, you want to have a good half dozen states interacting with each other. This is going to be a very easy way to do that, I think. And that's where I really think it's going to be the most powerful, even though in the paper, they try to push you on the really big stuff. In the paper, they're making a big deal about how big it can handle these, how large it can get, but I don't think that's personally where it's the most useful. Although I'll go into how you do it both ways in this lecture. So what's the basic idea in the Scheidegger and Bilionis paper? They basically use Gaussian process regression, and depending on the size of your problem, you might want to use active subspace or not. But most of the time, you won't want it, I think. But it's there if you want to use it, and I'll talk about what it is. And they're basically trying to approximate a value function. So basically, they're basically setting up a VFI, a dynamic programming sort of setup, and essentially they're approximating the value function at every step of the iteration with what we would call what's going to be called a Gaussian process regression. Really a Gaussian process, and then regression is the way you sort of update that. But there's basically a Gaussian process that's giving you an approximation for the value function at every step of the way. And it's just a really efficient way to store and update that value function, is essentially what it is. So it's sort of a hybrid, as we'll see, it's sort of a hybrid of dynamic programming and projection. Since the VFI part is a dynamic programming, Gaussian process regression, I'll show you, it can be sort of interpreted as a type of projection method. So it's sort of like you're sort of doing dynamic programming, but at every single iteration, you're kind of using these advanced projection methods to keep track of the value function, for instance. All right, so what's the big picture? Now we're gonna start with Gaussian process regression, right? What are we trying to do here? What's the actual algorithm that we're going to implement here for Gaussian process regression? Well, we're basically in search of a function v, which is going to take us from some high dimensional input space of dimension d into a single dimensional output space, right? So maybe this is an investment policy function. Maybe this is a whatever it might be, right? Or maybe it's just a value function, right? Essentially, the idea behind Gaussian process regression is that rather than treat v as a deterministic function, right, which is what most classical algorithms do. Most classical algorithms basically say, I'm going to treat, the function of interest as deterministic. I know what it is. We're basically going to form beliefs over the set of possible, this should be v's, not s. Going to form beliefs over the set of possible functions. And then we're going to update those beliefs with Bayes' rule. So it's a really simple idea, actually. It's like, well, it's kind of like bringing some Bayesian econometrics into the sort of structural sphere, if you want. It's like, well, I'm interested in finding a value function. I'm doing a value function iteration. I don't know what the value function is. So how about I do this? How about I just say, I have some prior over what the value functions are. I'm going to evaluate the Bellman equation a few times, and then I'm going to get some posterior for what the value functions are. I'm going to see what that is. And that's sort of big picture. That's basically what Gaussian process regression is. And how exactly we'll do that, I'll go through and show, but it's not a complicated thing, and it's certainly not something that's foreign to economists. I mean, economists are very familiar with this sort of Bayesian updating, right? So you basically start with some prior beliefs over, say, the value function. You're going to update that prior using, say, some Bellman equation and Bayes rule. Your posterior is then going to be some sort of updated guess in a VFI setting, and you're going to kind of just move to the next one. You're going to use that as your continuation value, and then you're going to derive a new continuation value, and you're just going to keep doing this. The one thing they do in the paper, though, and you'll see this when we get to the algorithm, I found this to be pretty important for making it efficient, is you basically, it's not true Bayesian the way that they do it in the algorithm, in the sense that every single iteration, you'll reset your prior, and you'll see what I mean by that when I get to it. So the iterations change because the continuation values are changing, right? But you're not actually updating your prior. Every single iteration, you're starting with a brand new prior, which is just completely the same as it was before. And the update's going to be different because the continuation values are different, right? You can do it the formal way. I was actually able to make it work that way, where you actually properly update everything every period, but it's very, very slow. You don't actually, so this is one of those things where, yes, you can actually do it, where you update your prior across iterations.
Is this, Zach, is this akin to the policy updating, where you only update the policy function, but not is that sort of an analogous?
I don't think so. What is that?
In the sense that, are you saying you never update your prior, not even every so often? Right. I mean, we have this policy function acceleration where we keep using the policy function for a while, and I misspoke. We update the value function, but we keep the policy function for a while.
Exactly. Yes.
And is that akin or complete? No. Okay.
No, it's not akin. What you're going to do is, even in your last iteration, you're going to keep the same prior, and you'll see that it's not going to ruin the approximation to do that. So it is something different than the policy function iteration that you described, that kind of Judd outlines in his book. Mm-hmm. So it's not going to be that. In fact, that actually works. I actually tried that because I wanted to see if it works, and it does work, but it's just much slower. It's much faster to just reset the prior every period, and you'll sort of see why that is. So it's not. I don't want to call it a true Bayesian implementation, because it's not really. But it works. This is what they propose. It worked pretty well. This is actually what I got hung up on the most. This is where I actually reached out to the author and was discussing it with him. Because the paper is not written very clearly. I'm not going to say that in the slides, because I've been talking to the author. The paper is actually pretty hard to understand, but the actual algorithm, I think, is pretty good. It's a pretty useful algorithm. But yeah, so you never actually update the prior.
Just a quick question on that, though. Yeah. How important is it then that you choose a good prior? Like how important
doesn't matter at all. Doesn't matter at all, and you'll see why. I'll show you a couple different priors that'll both work. And I found it the easiest way to do it is to start with a zero prior. I found it actually doesn't actually affect anything. You might just gain a small amount of time, because when you're working with dynamic programming, which is what this is, right? It's basically dynamic programming plus some extra stuff, right? Your convergence criteria is still going to be given by the underlying dynamic programming. So if you have some sort of contractionary setup, the contraction is basically going to shrink the accuracy of your approximation down to a level of convergence, but it converges geometrically, right? So it's basically going to start from the largest gap between, say, your old update and your current update, and it's going to shrink it geometrically, right? So even if you have a pretty good initial guess, even if your prior is not too bad, even if you're off by 0.1 or 0.2, it's still going to take quite a bit of time to traverse from 0.1 or 0.2 all the way down to your convergence, right? Because the basic idea is most of the time spent in a VFI is actually time that's spent where the policy functions are pretty close, or the value functions are pretty close to each other, and you're trying to achieve tolerance, right? It jumps very quickly from, say, a bad initial prior to kind of where it needs to be roughly, and then most of the time is spent going from kind of roughly where it needs to be to exactly where it needs to be. And that's true for a regular VFI. That's just a property of geometric convergence. So because this algorithm essentially uses a VFI inside of it, it has that same property. And so I have found, trying different priors, that the prior doesn't really matter. And in fact, the original paper, they always use a 0 prior. They never even try to use different priors. And so that doesn't actually make a difference for them. Yeah. So what is Gaussian process? This is essentially what we're going to be doing kind of at each iteration. We're going to be doing something like this. It's essentially an interpolation strategy. Like I said, you're going to you have a set of prior beliefs over the set of functions that you're interested in. Right? And then as you observe realizations of that function, you're going to update your beliefs. So here's a good graphical example, right? Suppose we just have a one-dimensional function, right? And our prior is basically that the mean is 0. Given some x, the mean is 0. The mean level of output is 0, and there's some volatility. There's some standard deviation. There's some dispersion in my beliefs about what the function value could be at that point, right? So here at the value of 0, the mean is 0. And then my beliefs about where the function could be, we're going to basically assume that they're Gaussian, that they're normal. And that's basically what the idea of Gaussian process regression is. So the assumption is going to be that your beliefs are normal. And then here we have, say, 2 standard deviations out, right? So 2 standard deviations out is about 2. So here we have, say, a standard normal as our prior in this case. So the function at every single point is a standard normal. That's our prior, right? And then we come and we say, all right, I'm going to show you some points from this function, right, that we know to be true, right? So I'm going to.
Is in this picture, do you have the true function somewhere?
No, the true function. No, we don't know the true function somewhere. Sorry, I should explain here.
No. We don't know it in reality, but have you drawn it somehow yet?
No. So the 3 functions here are 3 different draws from the distribution.
Got you. Okay.
Sorry. Yes, I'm sorry. I didn't make that clear. These are 3 just random draws from the distribution. There's going to be some correlative structure between the different f's across x's, and we'll get into exactly what that is. But there's some correlative structure that basically keeps things smooth. So they're not discontinuous or non-differentiable or anything like that. The correlative structure ensures that they're smooth. Here's 3 random draws from my prior. So you give me a random draw from this. They call this a Gaussian process. A Gaussian process is a function that's basically a random variable. Here's one, here's another one, here's a third one, right? But I could take as many draws as I want from this, right? I'm basically just drawing functions out of a random hat, right? Now you come along and you show me, okay, I'm going to show you the value of the function at 5 different points. I'm going to show it to you here, 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 and here. And now we're going to have you go into there, and we're going to have you update your beliefs from your prior to your posterior, given the functions that I showed you. And you would get something like this, right? Where there's still some uncertainty about the function because you don't know everything, right? There's a lot of regions that you're not sure of. But here's, again, 3 random draws from my posterior distribution now. And you can see there's certainty at the points that I know, right? But in between the points that I know, I'm not certain, but I've actually shrunk the variance considerably in my beliefs, right? And so the 3 random draws I'm drawing are closer together, right? And that's basically what a Gaussian process is, right? And you can actually kind of see here why the initial prior doesn't matter that much, because once you choose a particular point, unless there's some measurement error, which you're allowed to have, and I'll get into that, pretty quickly the function just deviates very far away from the initial prior. And that's another reason why the prior doesn't matter that much when you're choosing a prior.
Just another question on the prior. So as long as you have sort of like a large enough standard deviation that you allow for, you should be fine, because otherwise you might observe something that's outside of your the standard band, right? And yeah. I mean, so I think usually a standard normal is enough. I think most time they're gonna basically assume you're starting with a standard normal, and most of the algorithms that I've tried kind of have that basic assumption in place. And really, for us as solving this as structural economists, what we're most interested in is not even the bands on it, the confidence bands, but the actual point estimate that comes out of it. And we'll see that. And that point estimate is going to be pretty accurate, because even then, we're going to be doing this. We're not actually going to be doing the algorithm that they propose is not actually doing the Bayesian estimation or the Bayesian updating properly across iterations, right? In a given iteration, it's done properly. across iterations, you kind of reset things. So what exactly do those confidence bands even mean once you get down to the final iteration? They don't really mean a whole lot. So I wouldn't put too much stock in the confidence bands themselves and say the credible set outlined by your beliefs itself. Now, if you're using this for something, I mean, this might have an advantage if you're doing something more empirically oriented. I mean, I think one advantage that Gaussian process regression probably has over something like neural networks is you do have this Bayesian structure built in, right? So if you're more empirically oriented, you actually want to draw out some credible sets or something. You can actually do that if you're just using this to run some sort of a regression instead of using it to solve a structural model, where you can't actually do that with neural networks, right? So it's a type of machine learning that's probably going to be a bit more conducive to someone who's more empirically oriented than some of the other algorithms out there. But that's basically how it's going to work when we do this. And that's essentially what we're trying to do the whole time. So it's not a complicated idea. It's not an idea that's foreign to most people, right? But how are we actually going to do it? Okay, so we basically assume that we wish to evaluate the function at n in particular input points. So sometimes in machine learning, these are called training points, right? And sort of classical methods that we would use to solve these models, we would probably call these the grid points, right? So input points, training points, grid points, they're all sort of talking about the same thing. So I have a collection of points. I have n of them in this d-dimensional domain. And we wish to evaluate the function at those points, right? So before evaluating the equilibrium conditions, what we're basically going to do is we're basically going to assume that there's some model knowledge about f. Essentially, what we're going to do is we're going to assign a Gaussian process prior, usually a 0 prior, but the prior doesn't matter too much. And we're basically going to assume that there's some distribution of f. We're going to assume that there's some initial distribution of f. And then what we want to do is we want to look at the new distribution of f given the input points that we observe, right? That's the basic idea. And then some hyperparameters of the model that are going to govern how we update the Bayesian prior. Basically, essentially what we haven't specified yet is the correlative structure between these points, right? Because that's going to matter a lot for the Bayesian updating, is the correlative structure that we're going to impose between these points. And those are going to be governed by the hyperparameter theta. Right, theta is basically going to govern, it's basically going to govern two things at the end of the day. It's going to govern the correlative structure in our Gaussian prior, or in our Gaussian process. And it's going to govern any measurement error that's in there. And I'll specify that very explicitly. But those are basically, when you actually estimate the Gaussian when you do the Gaussian process regression, those are basically the sort of things that you're updating, right? Right, so those are the hyperparameters of the model are basically going to govern the correlative structure. So given the correlative structure of your functions, given some observed input, you're basically going to get a distribution for your posterior. And that's essentially what the Gaussian process regression is doing. Where m, this is the mean, which you're going to basically get a new mean. This is basically going to be a mean function, which you'll see, which is going to be our new mean function. So essentially, and then k is going to be another correlation matrix, right? So basically, when we do this, when we update our new points, we're basically, here our mean was 0. Now we have some new mean that's going to run roughly through here. I mean, all these functions are kind of close to the mean. And then there's going to be some new correlative structure, right? Because now the correlation between this point and this point is a little bit different than it was before because we've updated things, right? So we're going to get this new matrix. So given the hyperparameters theta are going to give you the initial prior distribution, and then the new correlative structure that's going to emerge is going to be given by this sort of K matrix, which we'll go into in a little bit. But essentially, what we're going to be doing is updating these thetas sort of every iteration. It's sort of going to be the hidden magic here is you sort of do a little maximum likelihood estimation in every single iteration, and that's basically the idea behind the algorithm. Okay, so the mean. This is going to be our prior mean, I believe. I believe this is a prior mean, if I'm not mistaken. Let me just check and make sure, or skip ahead here for a second. Yeah, this is the prior mean. Okay, so this is the prior mean. It's given by a function, m, which you can evaluate it at any x. Right. So if I evaluated my mean function, this m of x, that's my mean function. I can evaluate it at my input points, and that will give me a vector, right? So the mean is an entire function. The Gaussian process regression has this mean. And I'm going to pick a handful of points, and that's going to give me an n-dimensional vector of the mean evaluated at those points. And we're going to call that m, right? Little m, right? We're also going to have a covariance function, right? Which is going to be the correlative structure of those points, right? So I'm going to evaluate, and that's going to be where this was an n-dimensional vector. This is going to be an n by n square, right? And we're going to call this the cross covariance matrix. So the cross covariance matrix is going to tell me the covariance basically between point 1 and point n, right? So it's basically going to tell me this matrix is going to tell me the correlation structure between, say, this point and this point, or this point and this point, or this point and this point. So it's going to be a symmetric positive definite matrix that's going to be n by n. That's going to give me the correlation between these points is basically what it's going to be, right? And what are we going to...
Zach, when you say correlation between these points, do you mean the correlation between the functions going through this point?
Yes.
That's short for. Okay, got you.
That's what I meant. That's what I mean. That's exactly right. Not the correlations between the, I should say that's correct. It's not the correlation between the input points themselves. It's the correlation of the function evaluated at those points. Exactly. And this actually is going to come from, so this particular n by n matrix is going to come from a more general cross covariance matrix, which will basically would allow you to create, if you had n points and you wanted to evaluate them against another set of n hat points, you could create a whole matrix that would basically look at the correlative structure, basically of any input points. That's basically what all I'm saying here. Here is because we're looking at n particular points with the correlation structure between these 2 points. We're basically looking at an n by n matrix. But you could choose any set of points and evaluate their cross correlation with any other set of points, and they call that the cross covariance matrix. So if I had 2 sets of data here, if I had x, a set of observations x, and then another set of observations x hat, I could look at what they would call the cross covariance matrix, which would be an n by n hat matrix. That's basically going to give us all the covariance terms between all these different points, because they basically all have some relationship to each other. And then basically what this is going to do is it's going to keep the function smoother. It's going to give the functions maybe properties that you like them to have. So these are really going to be the Gaussian process is going to build a lot on these k functions, right? These little k functions. So these little k functions, I'm going to get into right now. These are referred to as kernel functions. So we're basically going to, a Gaussian process regression. So our sort of prior assumption, if you will, about the function is going to be able to be parameterized by an m and a k, right? The m is going to correspond to our initial pointwise guess. So what's our mean? So it's like, well, what's the average? Say you have a value function. What's your guess at the value function? That's going to be your guess at the average of the value function. And then what you're going to do is you're going to parameterize this cross covariance matrix with what we call a kernel function, right? And what that's basically going to do is it's going to tell you about the covariance relationship between 2 points in the input space, right? You have 2 points in the input space. You're going to get some covariance between those 2. And the kernel function is basically chosen to maybe give you some nice properties in the function that emerges from that. So the most common one, and the one that we'll start with, is just referred to as square exponential function, right? Which that's basically going to say that the covariance between 2 points, this is the function evaluated at 2 points, as Rudy was pointing out, say x and x prime, is going to be given by this term s, which this is like an absolute level term. They call this signal strength. So that's sort of the size, the size of the covariance between the 2, if you want to think about it like that. And then these L terms here, which these are the lengths, they call this the length scale. And this is basically going to say, and you're basically going to sum these up across all the different dimensions. So suppose I have a 2-dimensional problem. Right, so I have a 2-dimensional input space. Maybe I have capital and productivity, right? Essentially, one point in this input space is going to be capital productivity here, and then another one's capital productivity over here. And I want to know what the correlative structure between these 2 is. I'm basically going to pass it through this function. There's going to be a length scale that corresponds to capital. There's going to be a length scale that corresponds to productivity. That's going to tell us how much each of those dimensions contributes to the overall correlation between these 2 points, right? And this S term scales the whole relationship, right? So if S is very small, then, so L tells you the individual, the contribution to the correlative structure coming from the individual dimensions themselves, and S is sort of an aggregate that talks about all of them, right? So if S was 0, then there would be 0 correlation between these two. If S was positive, stronger, there's going to be more and more correlation between these two. But how much does each individual dimension contribute to that correlation between the two is given by the L's. So the parameter, the vector of hyperparameters is this signal strength, and then all these different L's. And you can see, right, that if X was equal to X was equal to X prime, right, this would be exponential of 0. That's just 1, so you would just have a variance of S squared, right? So S squared would also, what S squared is going to correspond to is that's going to basically be your prior variance, right? Because if you actually evaluate it at the same point, then that's going to give you the variance at that particular point. Whereas if you evaluate them further apart, you know, there's going to be, you can see that basically the variance, the covariance is going to, the correlation is going to shrink as you get further and further away. And this is actually designed such that, you know, you have a distribution of functions, and you want to draw from a point that's right next to the function of that's right next to the previous point, but not right next to it. This is basically going to ensure that the variance of that is going to be very, very, very small. And essentially what this does is this actually gives you differentiability in your prior functions, right? So any function that you draw from this process is going to be differentiable using the square exponential, right? It's not the only kernel. I'll actually go into several different kernels that you could use. It's sort of one of the most common first go-tos because it's pretty easy to work with, and most of the time it works pretty well. But that's essentially what it's doing, is it's basically giving you some correlative structure between the 2 points. The correlation between any 2 points decreases as you increase the distance between those 2 points. And S is basically going to give you the unit variance at a particular point. Right, so the Gaussian structure, so here this is also giving us our prior variance. S squared is basically going to be the prior variance at a particular point, right? But these length scales allow you to have a more general correlative structure between these points, right?
Sorry, Zach, quick question.
Yes.
If I understand it correctly, is it analogous to say parameterizing the sort of Hessian information of the objective function? Like it looks like it's just parameterizes like second order relationship between the points, right?
Yeah.
Like curvature information.
Yes. I don't think so, but I'm not actually sure. The Hessian information, yeah, I'm not actually sure. I don't have a good answer to your question.
Okay.
I mean, what we're doing here, here's the difference, I think. The Hessian information is going to be built off of the likelihood function, right? Which is going to come from some data, right? This here, this is our prior assumption before we go into it, right? So I don't think it's going to be the same as the information matrix and say some sort of maximum likelihood estimation routine, because we're going to specify this sort of correlation structure before we ever even look at the data, right?
Oh,
so basically,
I see. Yeah,
this particular K is telling us what the prior looks like, right? And then once we see the points, we'll update it, right? As we'll see, it's not going to be true Bayesian what we're going to do either, because we're sort of going to update. We're going to update these hyperparameters, even though these hyperparameters are actually governing our prior, right? So it's really not going to be a true Bayesian process either, because with the Bayesian process, you would kind of stick your initial beliefs and fix them and then update things based on those beliefs. But here we're actually going to try to tailor, if you will, we'll sort of tailor our initial beliefs in a way that Bayesians would not consider kosher. That's basically going to be one of the things we're going to do. So it's going to be a little bit more frequentist in some sense. Again, this is sort of, it's a bit of a messy algorithm, but it works in the sense that it's not really, it uses some Bayesian elements, but it's not proper Bayesianism. It's not really updating things properly, but it works very well. And so again, we go down to the docs, we get it done. No one has to know what happened down there, right? That's the basic idea, I think, behind this. Okay. Right, so the mean M is going to be given by that. We basically have a kernel density function sort of that's going to give us the correlative structure between any 2 points. All right. And as I mentioned before, this S is referred to as the signal strength. This Li is referred to as the length scale, right? So the larger is the length, so the higher is the S, the more overall variance you have. The higher is a length scale, the less or the more, because this is negative, it's a negative and then a denominator. So the bigger is the length scale, the more that particular dimension contributes to the correlation between points. All right, so if you have capital and productivity, if the length scale is really high for capital and really low for productivity, then basically what you see is that there's a lot more correlation coming from the capital across these points than there is coming from, say, the productivity, right? And that's basically going to be governed by the length scale. And there's as many of those as you have dimensions, right? Now, this is not the only type of kernel function. There's several others, and it's not the only useful one I found either. I've actually found that this works for some models, but not for other models. But there are other functions that work better that I'll get into a little later. But let's run with this for now because it's pretty simple. It's always positive. You can see how the matrix that would come out of it would be positive, definite, and symmetric. So it will work perfectly well for our purposes. So K would basically have a diagonal row of S squared. That's going to be basically the prior variance. Li is going to govern the contribution of input dimension I to the correlation across the points. And as X approaches X prime, that correlation approaches 1. So basically, you're going to get differentiable functions out of this. It's that much you can prove. With Gaussian process regression, you can prove that if you have this correlative structure as your prior, then you're going to get a different. Your assumption is that your function of interest is differentiable, right? You can't actually have a posterior function out of this that comes with something that's not differentiable. Right. So what do we do? What do we do now? So we have our prior, which is given by, what we've done now is we've set up our prior. We have a vector of thetas, which tells us the hyperparameters that basically governs our prior. And now we actually want to pick a few points, right? So we're going to evaluate the function at those points, and we're going to see what they are, right? So we'll call it T. These will be our training inputs. So we have our training inputs. We have n of these training inputs. We evaluate the function, and we get a handful of these. So maybe this would be a Bellman equation. We're evaluating our Bellman equation at, 15 different grid points, right? That's essentially what we're doing here. And we're going to then try to use these endpoints to extrapolate to the rest of the function. It's also going to be helpful to assume when we do this that we're actually, and this is just a pure numerical thing. There's nothing theoretical about this. It helps to assume that we observe the output with some measurement error, which they call SN squared. This is another confusing part of the paper. They say in the paper that Bayesian formalism requires that you have measurement error, which is not true at all. Bayesian formalism doesn't require that, right? Why they actually do it, and I learned this talking to the author, that it's just it basically helps that cross correlation matrix. It keeps it from becoming singular. Because when you're updating it, sometimes it might become singular, and this sort of rounds things out a little bit, right? It's usually not very big. We basically want to assume that we're observing the correct function, but there's just a tiny little bit of noise there. So we're going to assume that there's this noise here, but it's tiny. Think about it as more just being there to round things out and keep things from becoming singular, right? But we'll make sure that we account for it in the Bayesian updating is basically what we're going to be doing. So we observe this T, but maybe we don't observe it perfectly. We observe it with some noise, SN squared, right? So we don't observe a true function. We're going to observe the true function with a little bit of noise. So our actual observation is going to be what we would have seen in the function, given a little bit of measurement error here. So it's going to be the measurement error will be normally distributed. Here's the true function of interest, F, and that's the mean, but then there's a little bit of noise coming from this measurement error. And then we're basically going to estimate how big this hyperparameter is, how big the measurement error is, but we want to keep it really small. And that's actually going to be pretty important. Right, so given that, we can actually build up, given everything we have so far, we can actually build up the likelihood of given a particular observation T. So I basically evaluated the function at a given point, at a given set of training inputs. So I have some X, those are my training inputs. I have a vector of hyperparameters that govern the correlative structure, theta. This basically creates my prior. And then I have some measurement noise. Given that, I can talk about the distribution of what I observe, given all this information, right? And it's going to be normally distributed with a mean given by our mean function, our initial mean function, and a variance given by our cross-correlation matrix plus the measurement error. Is essentially what we have here. And this is our likelihood function. We can compute the likelihood of this particular set of T's, right? And here's the part where we're not really going to be Bayesians, in the sense that what we're going to do is we're going to observe the data, and then we're actually going to sort of update our prior, which is a little bit weird. But we're basically going to choose the thetas, which again actually technically govern our prior. We're going to choose those thetas to maximize the likelihood of our observed observations. All right. So we're going to
just to be clear. So every step now. So we have a standard Bellman equation step,
yep.
or whatever. Get some estimate of a point.
Yep.
And then in addition, we do another maximization step, yes, which is a sort of this estimation step.
Exactly. Exactly. Okay. Essentially, what this algorithm is going to look like, and I'll show it to you in a little bit. It's going to look like a standard VFI, and then at the end, we're going to do this estimation. And then we're going to update things using this estimation. Essentially.
And then you go back. That's the loop, basically.
That's basically it. It's a pretty simple exercise.
Okay.
So it's basically done by, we're basically going to assume that it's done with maximum likelihood. We're going to select the thetas to maximize the likelihood of the training data given everything else. That's going to give us a particular vector of a particular signal strength, a particular length scale, and a particular measurement error too. Although I find it helps to really confine the measurement error, because the measurement error can really throw things off. But I'll get to that when I actually go to the code. But you basically pick the hyperparameters to maximize the likelihood. This problem's pretty well behaved. So simple gradient-based methods tend to work just fine. They usually suggest starting from multiple points for robustness, starting from several different initial guesses for theta. Sometimes that helps. I haven't found it to help a whole lot. Maybe it helps with the really high dimensional stuff that they try to do. But I'll get to that. Essentially, you might want to use a couple different techniques to try to do this maximization. And you're basically going to get a new theta. You're going to get this theta star, right? You're going to get this theta star. Then you're going to combine what you observed with this theta star and this SN star. And you're going to get a new update for functions that will be, you can use this to derive an estimate for the posterior mean and the posterior variance at points that are far away from your initial guess, right? And this is basically just a Bayesian updating procedure, right? Essentially, your new mean is going to be your prior mean plus the distance between the output function, the output that you observed, and your prior mean, weighted by this cross covariance matrix term, right? So it's really, I assume the function mean was here. I observed it here. Based on the correlative structure I've implemented and found to be optimal, my new mean is gonna be here, right? And there's a similar way to update the cross covariance matrix. Although the mean updating is most important for us in the structural approach, because this cross covariance term doesn't really mean a whole lot in this context, because it's not really proper Bayesianism the way that we're all doing this, but nevertheless you can do it. The mean is what's important. This is basically going to give us a point-wise estimate of any function, right? This is actually just a continuous function, right? So it's quite useful, and this is basically going to be our update. Our new function is just going to be this, and so there's a relationship of this to projection methods, which is why I talked about a little bit earlier. Which is, if you look carefully at this posterior mean, which is just this thing here, you basically have, keep in mind this t and this m, these are just vectors. So what I've constructed here is I've constructed an entire function using an initial function that I had, my prior function. So that's a function I already have. And the cross correlation matrix here, which is actually a function of the initial of x, times a vector. So I've basically taken my vector of points of n points and extrapolated it to anywhere in the domain space. That's basically what I've done here. And so I use n points to extrapolate everywhere else. That's essentially this particular equation, what that's telling us, right? And so one way of looking at that is, if you actually, because this t minus n, that's just a vector, and this is just a matrix that you pre-multiply the vector, which is just the inverse of the cross covariance matrix plus the measurement error. That basically, you could think about that as actually just giving you a set of coefficients, right? And then if you apply those coefficients to the initial function k here at the beginning, what you actually get is that you get that what is your new guess for the posterior mean? You're actually building up a guess of your posterior mean based on the prior mean, plus some linear combination of the density of the kernel functions. So you're basically approximating the function of interest using a linear combination of these kernel basis functions. So that's the sense in which it's sort of like Chebyshev polynomials or Legendre polynomials or some of the other polynomial approximations, in which you basically have a linear combination of these polynomials building up your approximation. Here you actually have a linear combination of these kernel functions, which govern the cross-correlative structure between them. And this is actually the most efficient way to store them, right? You can basically just store a matrix of, you can just store a vector of coefficients A every time you do this, and then this function it becomes immediate to evaluate this function. So it's not, one of the really nice parts about this is it's very fast to evaluate the function itself, which is not always true for some functional approximations. And that's basically how it's sort of like a projection. You're building this up using a linear combination of basis functions, right? So typically, we're basically going to assume that the prior is 0, in which case this is 0, and you're basically building everything up from the basis functions. But again, it does work for any prior, and I have found that to be the case. Okay, so normally what we do in this class, since it's a pretty long class, it's like a 3-hour class, we usually will take a 10 or 15-minute break right around halfway through. And now is probably a good time for that. So let's take a little break. We'll come back let's come back at about 10:40. We'll take a little 15-minute break. Maybe get some coffee, take a little walk or something. And when we come back to this, now we sort of have most of the theory we're going to need now. I mean, all the new stuff we kind of have introduced here. What we'll do in sort of the second half of the course, I'm going to show you how we can go through and implement a lot of that stuff. I mean, what that's going to look like in practice, and we'll do it in particular for a very simple sort of consumption saving type problem. And we'll go through the code, and we'll go through a few other examples, and then I'll talk about some other stuff you can do on top of that. But the bread and butter of the theory is kind of what we just went over. So let's take a few minutes to let that sink in. Let's come back at about 10:40, and then we'll go through some of the code. We'll go through some examples of what this thing's going to look like and how powerful it actually is.
Hey, just Zach, I'm going to leave because I'll have to teach.
Okay.
At 11, so I'm not going to come back. But I just want to thank you. This has been great. I'm looking forward to seeing the rest. Thank you for providing the public service, man.
Oh, absolutely.
I'm sure we will all get into your office once we physically can again.
Yes.
And pester you with questions. Thanks so much.
All right. Very good. Well, I will see everybody else around 10:40 or so. So we'll take a little break. We'll come back. All right, we're back now. I'll give everyone a minute or two here to come on back. Okay, very good. So before that little break, we had just finished. Okay. So before that little break, we had just finished talking about some of this theory behind Gaussian process regression, which again, Gaussian process regression is just one algorithm, one type of machine learning algorithm. I'll discuss neural networks a little bit at the end if I have time. I'm not going to have any code on that because I haven't actually had a chance to implement that one myself. But I know a lot of economists have been using neural networks, and they're also very popular in industry as well. So I'll talk a little bit about the big picture ideas of what they are and how to build them, because they're not actually that complicated. But Gaussian process regression is one of them. We went over a little bit of the theory of it. And the basic idea behind the algorithm we're going to implement here is we're basically going to have a sort of a value function iteration, where essentially every single iteration is going to be, we're going to approximate every single iteration with a Gaussian process. And we're basically going to estimate a new process every single iteration. And that's going to serve as our approximation. All right. So to fix ideas, we'll consider a simple DSGE model. It'll be dynamic, stochastic, discrete time, infinite horizon, sort of your bread and butter macro model, if you will. We'll have some states that'll be exogenous and endogenous. So maybe we have, I don't know, productivity, maybe some demand shocks, maybe we have capital or foreign debt holdings, leverage, whatever you might want to throw in there. It's all in there. We'll have some control variables that are chosen from a set of control variables, C. And there'll be some law of motion for the states, given the initial states moving forward. And basically what we're going to want to solve for are the control variables in the law of motion. So we'll want to basically see how this thing iterates forward. We're going to have a Bellman equation, which is going to say that we'll have a flow utility. We want to choose the controls in the control sets. Maybe this is investment, maybe this is consumption, maybe this is some sort of government policy, whatever it might be. We want to maximize a flow payoff given the initial state and the control variables, plus a continuation payoff, which will depend on the states tomorrow. The distribution over those states can be affected by current states as well as the controls, is the basic idea. And the controls can lead directly into the states tomorrow. So the X prime, we could say choose investment today and have that pop up in the states tomorrow. That's perfectly fine. There's no problem there. It's just a standard Bellman equation. And then the equilibrium is going to be when the update is exactly equal to the function we gave it, right? So when V is equal to TV. So here T is a functional operator that takes an initial function V, passes it through this Bellman equation, and then gives you a new function. And we've achieved an equilibrium when those two are the same, when the new function we get is the same as the old one that came out, right? And then the optimal policy function is going to tell us what are the controls that you choose given the state that you're at. And so at equilibrium, we're going to get some policy function that comes from this maximization, right? So that's the basic environment. And essentially what we're going to do, the way to set up this algorithm in the full model is you're going to have an initial guess for the value at infinity, which I find it to be best to just set that to the prior, which is fine to set to 0. So usually I'll just start at 0, but you can start other places too. And at each iteration, what you're going to do is you're going to basically randomly generate what we call a small set of the training points, right? So how are you going to choose the grid? Initially, you're just going to do it randomly. And that's actually going to work for machine learning. All right. So you're basically going to pick a small set of grid points, and you're going to generate them randomly from the space of interest. So maybe I have some productivity, maybe I have some capital, maybe it's a 2-dimensional problem. I'm just going to randomly generate points in this 2-dimensional space, and those are going to be my grid points. Then we're going to evaluate the Bellman equation at those grid points. That's going to give us an updated T. That's going to give us our output, our new our output is going to be what we get from the Bellman equation. Say that. Then what we're going to do is we're going to estimate those hyperparameters from the model, and that will allow us to update this surrogate, what they call a surrogate function. That's basically the function that comes out after you do the maximum likelihood estimation. And then you apply those hyperparameters, you get a new posterior mean, right? Given by this function, this one here. This is going to be our new function, right? So we have some prior, which say is just 0. We're going to evaluate the Bellman. That's going to give us a t, and then we're going to update the new equation using that posterior mean. And then we just do it, and that we'll call that V surrogate. That's what they call it. They call it a surrogate function. The surrogate function is what you've learned from looking at the data. That's the term they use in machine learning. And we're just going to set our new update to that surrogate function. And then we're going to iterate again. Now, again, the important point here is that we're not going to reset the prior variance and the mean for each iteration, right? Or sorry, we're going to reset that for each iteration. So every single time, we're not going to use our new update as our new prior for the next Bayesian or Gaussian process. We're just going to continue to assume that it's 0, right? Like I said, I found before it actually works if you don't. If you actually update the priors every time, I have found that it works, but it's just very, very slow, and it doesn't really help that much. So this keeps it very fast, and this helps it work really, really well. The Bayesian updating together with the maximum likelihood estimation really just nails it exactly where it needs to be. So it's not really a true Bayesian approach, but it is a lot more efficient. So, and what we're interested in here is efficiency. And once you're done, or you could do this, you can either do this in each iteration, or when you're done, you can train other functions besides the value function. So here we're just talking about training the value function. Training is when you learn it and interpolate it. You can do that for the policy function. You can do that for all sorts of functions, right? I have some sovereign. One thing I really like about this is I've gotten this thing to work for sovereign debt models for reasons I'll talk about in a little bit, and that's something I work with all the time. And you can train price functions there. Price functions are endogenous equilibrium objects, no problem. You can train those. You can train all sorts of stuff, and it works pretty well. You can basically train any function you want to look for. So you can do this for multiple functions in an update. It doesn't just have to be the value function. Anything that's relevant. You know, maybe you have some sort of monetary policy function, some sort of fiscal rule, some sort of whatever that's endogenous. You can just train it just like everything else. And it doesn't take very long. Right. So for a policy function, you could either just wait till you're done, wait till it's converged, and then train it once, or you could train it at every step of the way. It's kind of up to you. The GPR is pretty easy to code yourself. As you've seen, we walked through the whole procedure. It's not complicated, but there is a package in Julia that allows you to do it. There are also packages in Python that let you do it. I believe MATLAB has packages that allow you to do it. I do recommend using these packages. It makes things a lot easier, and you wind up getting the same results. I've actually confirmed by coding it myself using these packages that they're doing the same thing, but they're actually usually significantly faster. I'm not entirely sure why that is, but they might have built-in solvers that do things better when you estimate. I think that's probably what it is. And there's less room for you to make your own errors. The code is very parsimonious when you use the packages too. It's very succinct. It looks very much just like a regular VFI. So I'll show you both of them though. So the first one we'll walk through, I'll go through and I'll show you all the steps very carefully. And then the next couple of examples, I'll just go ahead and use these packages. And you'll see that the packages are quite a bit faster. And they get you the same basic idea. Okay, and then how are we going to use our training inputs? Where are we going to get our grid from, basically? This is basically where we see that this is a machine learning algorithm. This is what makes this a machine learning algorithm, in my view. And that's basically that how many points do you need to generate when you do this? Every iteration, the answer they give is between 5 and 10 times the number of dimensions, right? So if you have a 2-dimensional, I usually will err on 10 because honestly, 10 is nothing, right? If you have, 10 times the number of dimensions. So for a 2-dimensional problem, that's 20 points. You're going to randomly generate 20 points in the state space. And you're going to build up your interpolation from that, which honestly, that's nothing, right? 20 points is absolutely nothing. That's especially if you scale this up. Like I'll show you a problem a little later that's a 5-dimensional problem. just 50 grid points. That's all you need to evaluate, which is mind-blowing. And you get a fully continuous interpolation along every single dimension with all relevant nonlinearities, which is mind-blowing to me. Because if you were to do that with SmallYAC or with classical methods, you would require thousands of grid points at least, maybe millions. The fact that you only need to do it with 50 is, I mean, this is where machine learning is magical, right? And I do mean that in the sense of the word, like magical. Like I don't think anyone really understands why this is, but it seems to be the case, and people have made a lot of money basically exploiting this.
Sorry, Zach, quick question.
Yes.
Just to clarify, so at each iteration we select those grid points randomly, right?
Yes.
And is it sort of like we choose it uniformly over the state space, or?
Yes. So I'm actually going to talk about this a little bit. In the simple benchmark model that they present, in the simple benchmark algorithm, they just have you draw it uniformly. This should just be one uniformly, not two. They just have you draw it uniformly from the d-dimensional cube of interest. That's not the most efficient way to do that. One thing I'll spend a decent amount of time on a little bit later in this lecture is how to get a better idea of where to draw it from in a way that's more efficient. Because I have found, especially for some interesting classes of models, essentially what the most useful algorithm I've developed from this, which is a little variant of what this is where you actually start to, in addition to estimating the model every period, you also simulate it for a little while. And what you can do from that is you can build up an ergodic distribution, and you can use that ergodic distribution, you can draw from it to get your new points. And that I found is very efficient and can handle all sorts of really interesting cases. But I'll get into that in a little bit. So for right now, the first example, we're just going to draw it randomly. But I think you're hitting the right point, which is that where you draw this from is going to make a difference for how long it takes to get there, how accurately you're going to be able to do this. And so, yeah. And so I have found that for problems that are a little bit more sophisticated than just the simple business cycle type model, it helps a lot to carve out a particular distribution that you're drawing from, to have it like the ergodic distribution. But yeah, every single iteration is a new random draw, which is also something that I found doesn't work the best in other cases, but I'll show you kind of some of the updates or changes I've made to the algorithm that I think make it work a little bit better, that mostly involve how you draw the training inputs. Because once you have the training inputs, the rest is straightforward. It's just evaluate the Bellman along all those training inputs, update using the Bayesian method, estimate the hyperparameters, and then update. It's really pretty simple. As I mentioned before, it's not always efficient, and this is what I was talking about with Georgi here for a little bit. When you have distributions, ergodic distributions, that are a little bit less well behaved, you can actually exploit that in machine learning, which is really cool. You can actually just draw from that, and I'll show you that very explicitly. And this is actually, I think, one of the most powerful parts of machine learning, is your ability to have this flexibility in the choice of the input points, because that's precisely what you don't have with a lot of the sparse grid methods like SmallYAC. SmallYAC only works because you choose the points very, very carefully, right? And here you can just draw them randomly from wherever you want. So it really allows you to adapt the flexibility of this algorithm to a whole bunch of different models, which is really cool. And I think it's one of my favorite parts about machine learning, because it's actually, I'm about 99% sure that, like I said, I work on sovereign debt stuff. And this is really why it works for sovereign debt, where a lot of classical models fail, I found, is for this reason, and I'll go into that. Okay, so to see an example, we'll do a couple examples here, and we'll walk through the code, and I'll show you how to implement this whole thing. Let's consider a simple consumption saving model with some uncertainty. Really simple, really bread and butter. We're going to have an endowment economy, so there's no production. We're just going to have this output that follows an AR1 process, or whose log follows an AR1 process, mean around 1. And there's going to be a level of risk-free debt, right? So what's your consumption? It's going to be your output minus the payment of old debts, plus the issuance of any new debts, right? So this is debt here. and you have some initial level of debt, you have some output, and then tomorrow you're going to have some distribution of output. You're going to take the expected value, and then whatever level of debt you entered with, right? And we're going to try to solve this with machine learning, just to show you an idea of how you would implement it, because it's actually pretty simple, right? So I have here some Julia code that does this. I'll try to make it as big as possible so everyone can see it. And you're going to see it looks pretty darn similar to a value function iteration. That's essentially what it is. But we'll choose some model parameters. I have an interest rate. We'll say it's a 5% interest rate. To keep things nice and stationary, I'm just going to go ahead and set beta to be equal to 1 over 1 plus r. We'll have CRRA preferences with a coefficient of relative risk aversion given by 2. I like to do this is something I recommend to my students. Flow utilities and things like that. If you have a function like CRRA or log, which can misbehave if it's negative, it's not defined if it's negative, or give you something you don't want if it's negative, to just go ahead and create an auxiliary function that deals with the negative cases and just sets them to a very, very large negative number. That can kind of help keep algorithms from, optimization algorithms and things like that from going haywire. So this is our utility function. We'll just go ahead and make it a function. This is the AR process for output. So we'll assume it has 1% volatility, which is, business cycle levels of volatility. 90% persistence. This is the unconditional volatility given this conditional volatility. Right? So this is a volatility of the innovations, and then this is the overall unconditional volatility of the output process itself. Right? D is going to be our number of dimensions. It's pretty easy to scale up the number of dimensions with machine learning because it only scales up linearly. But we'll go ahead and do it here because it'll be parsimonious the way we're writing a letter. So that's the number of dimensions. I'm going to set lower and upper bounds on output. So I'll basically go 3 standard deviations to the left for output and 3 standard deviations to the right. Unconditional standard deviations. We're going to vary debt levels between 10% and negative 10% of your average output. The number of inputs at any given, this is the number of grid points at any given iteration, and it's just going to be 10 times the number of states. So it'll be 20 in our case. So we're going to have 20 different inputs in each state. And then what we're going to do, and validate here, that's one thing I hadn't touched on yet, but that's just how you measure the convergence criteria. Did I talk about that at some point? Oh yeah. So to check whether this thing converges, the way they suggest to do it is because you're only using a small number of grid points, to make sure that one iteration is converging to the next, what you're going to do is at the end of this thing, you're going to draw 10,000 random inputs that are not the training inputs. So you just have a small number of training inputs, like 20 in this case. You draw 10,000 different ones, and then you evaluate your new value function and your old value function at all 10,000 of these different points, and then you take the average difference across those two, or the maximum difference, or whichever kind of criteria you want. And that's basically what we're going to do. So that's basically going to be how many, in the code, that's how many points are we going to draw to validate that we have convergence at a given point. I have a function here that's just going to draw from a uniform distribution output and debt, right? So output here, varies between YL and YH, and BH and BL. I'm just going to draw from a uniform. This is if I give it a random uniform matrix. If I give it a random matrix between 0 and 1, it's going to scale that up to the state space that I want it. So this is just a way of drawing. This scale mat function is just used to draw. I have my covariance function. This is my kernel basis function. We're going to use a square exponential basis function, just like we talked about earlier in the lecture. The first coefficient is going to be the signal strength. The rest of the coefficients, which are going to vary from the second to d plus 1, that's going to be our length scales. And what I would to get the kernel basis function, that's just s squared times the exponential of minus 0.5 times the sum of x minus x prime over L squared. And that's just these basis functions, right? We just got these, right? So I'm just writing that out. Right. I'm going to use some packages that I might need. So random lets me just seed the random variable so that I get the same simulations every time. I don't have to do that across iterations, so I don't need to reseed it every iteration. But I will do it at the beginning so that I get the same number of, say, iterations to convergence if I repeat the process, for instance. Stats functions, that allows me to use distributions like normal distribution, things like that. Linear algebras for matrix operations. This is the optimization package. And again, with Julia, all this stuff is open source, so you can just immediately get it. A plotting package and a package to take expectations. Fast Gauss quadrature just allows me to take the expectations. GR just sets the back end for the plots so we can see them. This is just some stuff to take expectations later on. It's just going to be useful for us. We're going to seed the random variable at the beginning. And here what I'm going to do, I'm going to keep track. I'm setting some large matrices here. I'll set a maximum number of iterations. It's going to converge before that. But there'll be the number of inputs, so it'll be the number of different draws that I have. And then that's how many rows it is. And then the columns are going to be each iteration. So this T is going to be, these are basically going to be my updated sort of Bellman equation. This is my prior at every one of those points. This is the correlation K matrix that came out from that. We talked about that in the lecture. That's the cross covariance matrix at the points of interest. This is a measurement error at each one of these iterations. So I'm basically making big matrices to store the stuff as I go along so we could evaluate them if we wanted to. These are all my training inputs. That's the grid points, basically. These are the hyperparameters that I've estimated at every point, so I can see what those estimates would look like. The likelihood of those hyperparameters at every point. And then this is the vector of coefficients, right? Because the vector of coefficients, I actually, again, when I project this thing, the actual projection of this thing is I can represent it as the new posterior can be represented as the prior plus a linear combination of these kernel functions, right? And so I'm basically storing all of these A's, all these coefficients, because those can be stored in closed form right away. That's basically, I'm just storing all that for every possible iteration, so I can update those and look at them if I want to. Here's my prior function, right? So this is the one I'm going to start with, right? What I'm showing you here is I'm going to assume for the prior, I'm basically going to assume, look, x, the prior is a function of x. X is going to be y and b in this case. It's going to be a vector with all the different states lined up in it. Okay. V prior, I'm going to assume that if output minus debt service at the risk-free rate is negative, which it's never going to be, but it's just sort of to check it based on the bounds we've set, I'll go ahead and make that a large negative number so that it doesn't crash. But if it's not that, then my assumption is going to be my prior guess on the value function is going to be that I'm going to maintain my level of debt forever. Basically going to say my policy, I'm going to assume that my policy is to set new debt issuance equal to current level of debt and do that for all of time from this point onward. And what that would do is that would basically say, well, my flow utility is just going to be output minus debt service for this particular level of debt. And it's just going to be divided by 1 minus beta because I'm doing that forever, right? And this is a rough approximation too, because it doesn't account for the uncertainty introduced, but you know, it's just a prior that gets us in the ballpark, right? Turns out this prior doesn't actually matter, right? We could actually just set it to 0 and we lose almost nothing. But I'll go ahead and do it so you can see how the initial one varies from the posterior one at the end. But that's our prior. Our posterior is going to be, we start with our prior. My final posterior is equal to our prior, and then we're adding the linear combination of these basis functions, right? Right, so the posterior is going to use the coefficients. That's the A. X is going to be on my input or my training points. And theta is going to be my hyperparameters. So given these hyperparameters, given these training points, I evaluate at a particular X this thing. And so this little function here basically just does this, right? That's all that it does. Okay. Right, and then we'll start off by just assuming that we don't have any of that stuff, which is basically going to be our prior. So we're basically going to assume that we're going to start our VFI assuming this prior. I won't have any smoothing or anything. So then we actually get into the VFI. So they recommend a convergence of 1 times 10 to the minus 4. It's a little bit bigger than the convergence that's preferred in the literature. I have found that machine learning can't really get accurate level is a whole lot smaller than 10 to the -4, unfortunately. It gets there really fast, but adding more training inputs doesn't really help that much. There seems to be the machine learning, at least for the Gaussian process regression, and it seems to be true for other algorithms as well, has this really rapid level of a really nonlinear level of accuracy that you really just jump up to a super high level of accuracy very quickly. But the marginal accuracy you get from adding more and more points is pretty small after that. So you can't just add a whole bunch of points and expect to get it a lot more accurate. There's kind of a ceiling on how accurate it's going to be. That's just something I found playing with it. They don't really seem to admit that in the paper. But I've tried a bunch of different stuff. It's a little bit of an unusual convergence criterion. It's a little bit bigger than normal, and the authors don't really talk about it. But my sense is that you can't really get it a whole lot better than this. But, you know, I think for most purposes, it's fine. It's still pretty darn accurate. I don't think anyone's really going to bat an eye at it. But I don't think you can really get it much more accurate than that. At least that's just based on my playing around with it. But we're basically going to iterate until the distance between updates is less than the convergence criterion, or we hit some maximum number, which we won't. All right, so the first thing we do, we start this iteration procedure. We're going to draw our inputs first. So the first thing we're going to do is we're going to draw all our points. So we're going to randomly generate points from the state space. So here I'm just randomly generating a matrix of two-dimensional uniforms, and I'm generating 20 of them from my 20 different inputs. And I'm going to scale them to the appropriate region of the state space. So I'm going to scale it such that I'm near in the relevant range for Y and in the relevant range for B. Right? And then I'm just going to save this if I want to look at it later. Right? The next thing we're going to do, we're going to set the prior means. So I'm going to compute my prior. I'm going to set it to, I'm going to compute what my prior is at these inputs. And my prior is, again, this function that makes the assumption that you keep your current level of debt forever and that there's no uncertainty after that. That's my prior. I'm going to evaluate that for all these m's. And then I'm going to actually do the update. Well, I'm actually going to, at this point, I'm going to get my realized function. I'm actually going to pass it through the Bellman now, right? So here's just a standard VFI. I'm going to do it for every one of these points I just drew. I drew a bunch of points, and I'm just going to evaluate the Bellman equation for each of them, right? So I'm going to go through. My first input is going to be my level of Y. My second input is going to be my level of B. I'm going to take an expectation using the Gaussian quadrature method over realizations of Y tomorrow. So this is just me taking the expectation. Given a level of B prime. So I'm going to define, so the way I do this is I say, I'm going to define the Bellman equation fixing B prime, and then I'm going to optimize over B prime. So that's going to be my way of maximizing, right? So given a B prime, this is my continuation value. VML, that's my current understanding, my current guess for the value function is ML is machine learning. So VML is my current guess for the value function. Take the expectation over that, given that I'm selecting B prime. This is just taking the expectation to get the continuation value. This is just a Gaussian quadrature thing. There's earlier lectures on this stuff if you want to go back to it, but it's just a continuous way of taking expectations. And then I'm going to return my flow utility, which is Y today minus B today plus B prime, plus beta times the continuation value, which depends on B prime up here. So, you know, I issue more debt, my flow utility goes up, but my continuation value goes down. Pretty simple concave problem. And I'm just going to select the best one. I'm going to minimize the negative objective function here in the range BL to BH. And then I'm going to call that T. I have a smoothing parameter here, but I'm not using it. So this is just set to 0. So this is just basically I get the negative of my optimum here. That's the maximum then is my value function. So my new value function is going to come into this T. This T is going to be basically the new Bellman, the Bellman update. So the Bellman update is coming into the T. Then what I'm going to do is I'm going to do this estimation thing. I'm going to estimate the hyperparameters. All right. So I'm going to build up a negative log likelihood here, and I'm going to minimize that thing because most built-in solvers are minimizers. Given some hyperparameters. So given a set of hyperparameters, which the hyperparameters are actually given in log space, and I'll explain that in a second. So I'm going to transform the hyperparameters from log space into kind of regular space. It's just 10 to the power of these different parameters. I'm going to construct my K function, which is just filled with these kernel density functions, given the hyperparameters that I've chosen. And then with that K function, and then the estimated SN, the estimated measurement error, I can construct the log likelihood. I just evaluate a multivariate normal PDF, the log of it, which is just this. That's just the log of the determinant of sigma, which sigma is just K plus the measurement error. And then I'm going to have this quadratic term involving the sigma as well. So this is just, if you just evaluate a multivariate normal PDF, if you take a log of it, that's what this is, right? And so I'm just going to return that. And it's actually the negative log likelihood, right? So I want this thing to be as small as possible. So I'm going to minimize it then, right? Right, so that evaluates, given a set of hyperparameters, that's the likelihood, the negative likelihood, for my given t's that I already chose, right? Right, so what am I going to do at this point? I'm going to take a guess at the initial parameters. So I'm going to assume that the length scale is about, or that the signal strength is about 0.4. The length scale for output is about 0.5. Length scale for dead is about 0.5. And that the measurement error is pretty small, 0.00001. You want the measurement error to be small, otherwise you're not going to get proper updates. It kind of has to be small. But it's helpful to search in log space, because basically what you're searching over is the coefficients, you know, so you could, you know, -5 is 1 times 10 to the -5, you know, 4 is 1 times 10 to the 4. So you might want to search very broad. I found, and the authors have found as well, that it's helpful to search in log space as opposed to just your standard space, because you can just traverse way more area that way, and that can be helpful, because sometimes you might have, you know, very large signal strength, because you might, one thing that can happen too is you can have multiple local maxima. And so you might have one that has a very large signal strength and very low length scales, or another that has very low signal strength and very large length scales. There can be multiple local maxima here, and that can arise sometimes. I've never really found that to make a difference for the updates. I mean, the updates are valid either way. The authors seem to care a lot more about this. The authors kind of recommend that you do this a bunch of times and that you take the best of them. There's no theory that says the best is that one is going to be better than the other. I mean, yeah, the likelihood will be a little bit higher, but both of them are going to be perfectly valid functional approximations. So the authors make a big deal about doing this, about solving it multiple times, taking multiple likelihood, doing multiple maximum likelihood estimates from different points. I've never found this to be a big deal. I'm going to do it here because the authors kind of suggested it. But it really makes very little difference, I found, whether you just maximize once or whether you maximize several times, because there's no theorem that says you need to have the global maximum for this to work. I mean, you just want a set of hyperparameters that does a reasonable job, right? So, I mean, if the theorem rested on if there was a theorem that rested on the global max, this would be a lot more concerning, but there's not. I mean, so as long as you get something that's doing a good job, it doesn't really matter. So I have not really found this to be a crucial step. The authors spend a lot of time talking about it. But yeah, so we'll do it here because the authors talk about it. So again, we're searching in log space. So I'm going to look at parameters varying from an order of magnitude 10 to the -9 up to an order of magnitude 10 to the 4. I'm also going to put an upper bound on the measurement error of 1, 10 to the 0, which is 1, because you don't want the measurement error to be too big. Because if you estimate a big measurement error, then nothing else makes sense, right? The Bayesian updating is just going to assume it's all measurement error, and you're going to get no updates. So I have actually found that you usually want to keep this pretty small. Even 0 is way too big. I mean, it works here, but it doesn't work in other cases. I usually need to shrink it even more than that in other cases, but I can get it to work just fine that way. So what we're going to do then is we're going to basically maximize it 5 times. I'm basically going to count 5 times, and we're going to optimize the likelihood, choose a vector of hyperparameters that does that. And that's basically what this is. I'm just optimizing the likelihood with these bounds on where it is, because I don't want it to get too crazy. And then the next time around, I'm gonna draw new parameters, just randomly generate parameters within these bounds, within these log bounds. So I'm gonna try 5 completely different parameter initial guesses for the parameters, and then do maximum likelihood on each one of those, and then pick the largest, right? So that's basically, we're going to do that. We're going to do it, 5 times, 10 times, whatever it is. Find the one with the biggest likelihood, and that's going to be our hyperparameters. And then once we do that, we just update, right? So theta total, this is just, here we get the K evaluated at the optimal hyperparameters. Here's the measurement error at the optimal hyperparameters. And here's our coefficients, the implied A's that come out of the optimal hyperparameters. And then what I'm actually going to do here is before I update it, I'm going to go ahead and check for convergence. All right, so here I'm actually going to update the function using these hyperparameters, using these new hyperparameters. That's what this is. Before I do that, I'm going to randomly draw 10,000 points, and I'm going to evaluate the old function at those points. Right? And then I'm going to update the function at that point, and then I'm going to evaluate them at those exact same points with the new function. So this is going to be the old update versus the new update. Right? And then I just check for convergence. How close are these, right? So I'm basically going to look at the average distance between the old points and the new points. And if it's less than 1 times 10 to the minus 4, then I'll declare victory, right? Right, and that's that. I actually ran this a little bit earlier just to make sure that it was working here. So I actually have it. You can see, so what I have here, this is the iteration number. This is the distance between old update and new update. So this is a value at a particular point, so you can see roughly where it is. So this is the value kind of close to the steady state, what the value function is. So my prior guess was not too far away. And this is actually the estimated measurement error. Because a measurement error, you kind of want that to be pretty small, or else your Bayesian updating is not going to work. 5 here, this number, that's just how many times it actually conducted the maximum likelihood estimation. Because sometimes it runs into an error and it has to do it 6 times or 7 times. So that just gives you an idea of how long it's taking. But you can see it converges geometrically, just like a regular VFI. That's basically, it's just a regular VFI. It's going down, and it converges down to, it hops around a little bit toward the end, and that's what I was talking about. The accuracy kind of is a little bit bounded, but it gets down to the region where we want it to be within about 85 iterations. I think I had something that keeps track of the time here too. Maybe I didn't. But this particular one is a little bit slow. It's definitely not the fastest way to do this particular iteration, as you would imagine. I mean, a standard VFI is going to work better for this little problem, right? Because you don't need to do this 5 maximum likelihood estimation thing in the middle of it, right? So that winds up taking some time. I think this maybe takes like a half hour or something to do. It's not a super long time. But there are way faster ways of doing this, right? The point here is not to show that this is the fastest way for this particular problem. It's to show you roughly what this thing is going to look like and how you basically do it, right? And so we can see some of the values that come out of this, like the one thing I'll actually show you real quick is we can see the value functions that it converged to. So I'm going to show here the value function that it converged to, as well as our initial guess. All right, so I'll go ahead and plot that here. Right. Let me try to make this bigger here. There. So there's our value function. The blue one is the blue one's the one that it converged to, and the red one is our posterior. So we can see our final result, basically. So we're definitely different from our initial guess. And you can see the same thing for the levels of debt. So that's across output. So this is a value of output. This is a value. So in particular, we're a lot flatter than our initial guess. We're doing the consumption smoothing. The consumption smoothing is a lot more powerful here than it is when we took our simple do the same thing forever strategy. That's basically what that's showing. Value functions across debt levels of debt. So here's high levels of debt, here's low levels of debt, so it's decreasing. You're a lot less worse off here than you are before because you're managing your debt a lot more. You're managing your debt a lot better by not just blindly choosing the same level of initial debt every single time. Right. So that is that. And you can kind of see like the points it's drawing. So if we went to like X total, so you can see our grid points, X inputs total, for instance. This is going to tell us this is going to tell us the points it's drawing. So you can see it's drawing, you know, 0.96, that's an output, 0.99, that's an output, 1.06, that's an output. Here's a level of debt, 0.09. Here's another level of debt, negative 0.01. Here's another level of debt, 0.07. And we have one of these for every iteration. There's 20 of these in every single iteration. So I was just storing all of those. And you can see the value functions as it goes every single time and everything too. And so, yeah, so it works just fine, just like a regular VFI. Converges, it kind of operates as you would expect a regular VFI to operate. There is a package for it though, which works a little bit better, I found, and I'll use this package for the rest of the class here. But I just want to give you a sense of how the package works. The package is basically going to create Gaussian processes as objects to be played with. And so in doing so, I'll give you an example. Let's take a much smaller problem. Let's take just a one-dimensional problem. All right. I'm going to have a couple of x's here. They're going to be, I'll take 3 input points for my x. I'll have 0.2, 0.4, and 0.54. So I've got a couple of points in the range 0 to 1. Here's a couple of functions that go with that. So at 0.2, the value is 1.2. At 0.4, the value is 2.2. And at 0.54, the value is 1.1. All right. I'm going to set the prior of this Gaussian process to be 0, mean 0. This is just part of the Gaussian process package. I'm going to set the kernel to be a square exponential kernel. That's the one we've been working with this whole time. And that's just set by square exponential kernel. The hyperparameters here, we have our signal strength and our length scale. Now, this is just a one-dimensional problem. The length scale is just, there's only one dimension to worry about. But normally that would be, you know, your signal strength and then a d-dimensional vector for the length scale. And we'll do some other kernels here too. I'll show you some other kernels. I'm going to assume that the observation noise is on the, this is the order of the observation noise. Just like I did in the code up above, everything, all the parameters that this code, that this package accepts are log 10 parameters. So you tell it a number, you're actually telling it an order of magnitude and not actually the number itself. So this is -8, that's the observation noise basically. So it's a very small observation noise, close to machine level. And then I'm going to create a Gaussian process that's going to use these hyperparameters, right? So the hyperparameters here are in log space. So this 0 actually means that the length scale is 1. So it's 10 to the 0. So the length, the signal strength is 1. The length scale is 1. That's basically my prior, right? I'm going to impose that, right? So GP, I'm going to have this sample. I'm going to create a Gaussian process using the sample x's, the sample y's. I'm going to assume a 0 mean, and I'm going to assume a prior correlative structure using these particular hyperparameters and this particular observation noise, right? And so it has a Gaussian process object. It's a one-dimensional object. There's 3 observations. And these are the hyperparameters, right? 0 and 0 at this particular point. Those are the outputs. That's the observation noise. It's already telling me the likelihood, given my hyperparameters, this is the log likelihood of the data that I see, okay? So that's not the best log likelihood. I could actually do better than that. I'll show you in a second. But one thing you can do that's kind of cool is you can actually plot the Gaussian process directly. So you can actually plot it and see what it looks like. So here we basically have 3 points, this one, this one, this one. And it's fitting this curve using just using the parameters I gave it. It's not actually estimating any parameters yet. It's just using the parameters I gave it. So it started with a 0 mean. And now the mean is kind of parabolic, right? So this is the mean that's running through it. That's its guess at the mean. But what you can do now is you can actually tell it to optimize by itself. So rather than going through and doing the optimization yourself, I'm going to set a lower and upper bound for the kernel parameters. So this is the signal strength and the length scale. Order of magnitude again. So this is, you know, I want it to be bigger than 1 times 10 to the -5 and smaller than 1 times 10 to the 6. And I want the noise to be between 1 times 10 to the -11 and 1 times 10 to the -6. So this is me setting bounds for the parameters. And then you can use this optimize function, optimize exclamation point. I want to optimize this Gaussian process. I want the bounds on the noise to be here, and I want the bounds on the kernel parameters to be there. And it estimated it for me. Successfully got new parameters. And our original parameters were 0, and our new parameters are not 0. -8.5, -1.7, 0.1316 or something. So now I can see what the new regression is going to look like. That's the new regression. right? Which is a little bit different than the first one because we optimize the hyperparameters, right? And it's also got, here it's showing us the 2 standard deviation confidence bounds, basically, for our points of interest, right? How would you use this to interpolate? Well, all you have to do, there's a function called predict y. So predict y acts on a Gaussian process, and it's going to tell you the pointwise mean of that Gaussian process, right? I've often found that for some reason in Julia, and this may be different in other languages, it will only take vectors of observations rather than a particular observation. So sometimes I have to add extra observations to actually do the prediction that I don't need. But, you know, be that as it may, we're basically using predict y here. So this is a function basically that is going to actually give me this quadratic looking function here, right? And it's not actually quadratic. It's a little different than quadratic, but, you know, it's kind of looking roughly quadratic. But it's very fast, one thing you'll see. I'm going to actually check this thing at some other point, say 0.3. So around 0.3, we should be getting something a little bit bigger than 2 here. 2.02. And we can actually see how much time it took to do that. I don't actually need this plot in here anymore. I don't know where my REPL went. There it is. So it took about, with Julia's just-in-time compilation, the first time you do it always takes a little longer. So the first time I do it took about 0.06 seconds. But if we run it again, you know, it takes 0.00002 seconds to actually do this. So it's a very fast evaluation of the function, which is one really nice part. And you get a value that's a little bigger than 2, which is what we were looking for, right? So this particular package is really nice. They have it in Julia, they have it in Python. I believe they have one in MATLAB too. I would highly recommend using it. I'll kind of show you in detail how we'll use it here for the next one we're going to do, which is one where we're going to get quite a bit more action in terms of the size here. So now we're going to have a slightly larger problem, one that's more suited for machine learning, because that was kind of a simple problem to fix ideas. So let's go to here. We'll have a production economy with adjustment of costs. So here we're going to have, I think I actually have some slides for kind of what we're looking at here, like a standard neoclassical growth model. So let me pull up kind of, just so we can fix ideas, kind of what we're looking at here. This one here. So we basically have an Euler equation. So think an RDBC model. We have an Euler equation. There's going to be, let's do it with a TFP shock. I think I have one with the TFP shock here somewhere, just to fix ideas. Here we go. Okay. So I have an Euler equation, which is marginal utility today is beta times the marginal product of capital times marginal utility tomorrow. And then we have a resource constraint, right? The resource constraint is just output. Output plus non-depreciated capital is consumption plus capital tomorrow, right? So I don't want to spend too much time on that. That's basically what we're doing, but we're going to do it with multiple sectors. So we're actually going to have 4 sectors. So we're going to have a TFP shock. There's going to be 4 sectors. They're going to be additively separable, the sector. So output is going to be additively separable in 4 different sectors. That's just going to give us well-defined steady states so that the dynamics are clean, theoretically. So output is going to be, we have 4 different levels of capital. There's going to be nonlinear adjustment costs along each dimension. So the rest of this is going to look pretty similar. We're going to have the same sovereign utility. I'm going to use beta a little bit smaller here. I'm going to set it to 0.8. So this is pretty impatient. But what I want to actually do is I want to just go ahead and set it running here while we go through it. So you can see it converge, actually. And it'll converge a little faster with a lower beta, because that's just dynamic programming. But we'll have the same level of volatility, a TFP shock with 1% volatility. These are just the production parameters for the different types of capital. I'll kind of assume that they're all symmetric sectors. Now there's adjustment costs across each, so it's not super trivial necessarily. There's different levels of depreciation across the different sectors. We have steady state levels of capital. That just helps us build up the grid a little bit. There's different adjustment, the sizes of the adjustment costs are different across sectors. This is a 5-dimensional problem. We have lower and upper bound on output. We have lower and upper bound on all the other ones. I'm going to keep it fairly tight. Again, I'll talk about this a little bit more in a little bit. So we're not going to have a huge grid here, although it doesn't really converge very well with a much bigger grid than this. And I'll talk about some solutions to get around that. The ergodic distribution trick really works very well. So I highly recommend that, and I'll go through that in just a second. But we'll have a fairly tight grid here. It's going through and it's doing it. The number of inputs is going to be 10 times the number of dimensions. In this case, we have 5 dimensions, so it's going to be 50 different points it's drawing from each time. And then, yeah, scale mat that just draws from the distribution. Everything else is basically the same as we were doing before. I'm not going to carry around as much stuff anymore because the Gaussian process thing is going to be all built into the package. I'm going to start from a 0 prior this time instead of a bigger prior, because that's going to be easier to hand to the package that way. You can see how well it's doing it. It's doing these iterations each time. Yeah, you can see how well it's actually doing. I'll come back to this, but you can see it's moving along pretty fast for such an enormous problem. This is a really big problem by most classical standards, and it's just handling it beautifully, right? I'm actually going to keep track of how long it takes, and then we do the iteration. What's the iteration? We draw our points randomly. Now we have 5 dimensions. We have 4 levels of capital, and we have output, and we have basically productivity. Output today is going to be productivity times all that capital. We have to choose, our choice vector is not just one dimensional anymore. We actually have to choose all 4 levels of capital for tomorrow. So we do that. Everything else is the same we were doing before, just a much higher dimension. There's adjustment costs to all of this. So if I have a certain level of adjustment across any one of these dimensions, it matters. And then I get some continuation value tomorrow. I have to optimize at all 50 points, a 4-dimensional optimization, not just a 1-dimensional optimization. But then I update the same way. Once I have that, then I have my new T's. I can then do my Bayesian updating that way. What I'm actually going to do is right here, I'm going to go ahead and check for convergence. I'm going to draw some random points to check for convergence. I'm going to start with the old function before I update it. And then my new function, rather than doing all that stuff I did before, I'm just going to let the Gaussian process package do it. So I'm going to set, these are my hyperparameters, the lower and upper bounds on my hyperparameters. So here I'm going to have the length scales for kernel, for the squared exponential kernel. Here's my signal strength. Here's my measurement error. I'm going to put reasonable bounds on all of this. Notice the noise has bigger bounds, or has much smaller bounds. I need to make sure that the noise stays small, or else the noise is going to take too much. It's going to take up too much. I'm going to set a Gaussian process that uses my inputs that I generated randomly, and then the Bellman equation output, starting with 0 prior every single iteration, using the kernel density given by the squared exponential and a certain noise. I'm going to go ahead and optimize that prior. And then I'm just going to re-optimize it 4 more times. That's all I'm going to do. And then I'm done. Then I'm just going to predict my new function using that Gaussian prior, the best hyperparameters. And then I'm going to run the convergence. I'm going to use my same convergence criteria points with the new update, and then check for convergence, and then start this thing over again. And you can see how it's going. We're getting there. It's 32 iterations in. It's starting to get pretty small. Things are starting to get pretty close. What I actually have here, I'm showing 3 different times. The first column here. So this is a sample value, something near steady state. This is the convergence point between them. This is the convergence metric. I have 3 different times. This is how long it takes to do the VFI part. That's the actual evaluating the functions. This is how long it takes to estimate the hyperparameters. And this is how long it takes to draw the points for convergence. So you can still see that with the new packages, with the Gaussian process package, it does the hyperparameter estimation pretty quickly. It's doing, what is this? This is it's D+2, so it's a 7-dimensional problem. We're doing 5 different 7-dimensional problems every single time, but it's doing all 5 of those in less than 2 seconds. It still takes more time to evaluate the Bellman than it takes to estimate the parameters at these higher levels. And it's almost done. It's almost converged, because again, the convergence criteria is 1 × 10⁻⁴. So within the next probably 30 seconds or so, this thing's going to be done. Which really, if you had showed me this, a couple of years ago, I wouldn't have believed that you could take a problem this big and just sit around and watch it converge just on your local desktop. Normally, you would take a problem like this, use a really fancy, sophisticated algorithm, hand it to a supercluster, and come back in an hour, right? The fact that you can do something as simple as this using just a simple VFI and actually get something nice out of it that makes a lot of sense is pretty crazy to me. This really is, it's a very powerful technique. It's about to converge. You can see it's not quite converging completely monotonically as we get down here. Again, that's where I found sometimes the accuracy is not super great. I don't think the accuracy is quite comparable with some of the classic methods. It sort of hits a point where it struggles to make it more accurate. And I think the authors kind of intentionally chose this point. That seems to be where I found it to happen. But you know, it gets there. And now it just converged. It's done. So we can see how long it took. Where's the workspace? It'll load here, the workspace, in a second. And it'll tell us all the values we need to know. But it'll actually tell us the total amount of time it took to run. And it's pretty fast. It's pretty amazing how quick it is. So Julia can take a little bit longer sometimes in other languages to finish things up because it's doing a lot of compilation along the way. The thing about Julia is it has this just-in-time compilation component where it compiles things as it runs them. So it's a little slow the first time, but it's often much, much quicker the second time that you run it. So that's why it can take a little bit longer to kind of, it's the little bar here just shows that it's still kind of finishing things up with its compilation. It's also getting ready to do plots. So there's some plots I was going to have down here, which I really don't think we'll need to see. It's just kind of standard. We're going to get the same sort of figures we saw in the simple consumption saving model. It's not really going to look any different. But just underlying it, there's just way more going on and a lot more to take care of. But the machine learning can handle it no problem. So while that's happening, I did mention before that they have this, I had to use a fairly tight window. I could only go kind of 8% below and above each steady state in order to get this thing to work. It's a bit of a drawback. You might like to have something a lot bigger than that. You know, something like perturbation methods, just taking Taylor approximations of the economy will usually get you reasonable estimates in that sort of range. So I do want to show you something where that can kind of help along this dimension. And that's this idea of building up the ergodic set and using those as training inputs. So whether you have a normal state space or if the state space is what they call irregular, which basically just means that the ergodic distribution looks a little bit funny. Uniform draws at each iteration are not going to be super efficient. Especially because you might have to tighten that uniform box pretty tightly to get the convergence level that you want. Whereas you can actually have a much wider box if you're kind of focusing on the part that matters. So what the author suggests is the following, and I definitely find this to be useful. That's at every single step, you're going to do at every single iteration, you're going to do one more thing. You're going to simulate some law of motion. So you're going to solve the model. That's going to give you a law of motion, right? A policy function is going to imply a law of motion. You're going to simulate that forward for, say, n periods to derive an estimate of the ergodic distribution. You're going to basically just build up a histogram of the ergodic distribution. Then you're going to fit a histogram to that ergodic distribution, or you could maybe do a Gaussian mixture model or some other way of fitting a distribution. It doesn't really matter what you do. But you're basically going to get an ergodic distribution, and you're basically going to draw your training inputs from that ergodic distribution on your next iteration. So you'll get a much tighter estimate. All right, so you kind of wind up getting this thing right where it counts, right? This I found to be tremendously helpful. That's really helps you get convergence a lot more quickly because again, there's sort of a bound on the accuracy I found you get from these things. And so if you can just really shove it into the area where it matters, that works really well, especially because it's very flexible in that area. You don't need to have a particular allocation of grid points to get this thing to work. So I have found, this is not stuff that's in the paper, but these are things I found. I found that there's kind of two things that help this thing to converge using this ergodic training set thing. And that would be kind of after you kind of get close enough with your iterations where the convergence is pretty close, but not quite where you want it to be, then stop drawing the inputs randomly, just fix them at a certain level. So fix them at a certain point from your ergodic distribution, from your current ergodic distribution, whatever it is, and just keep those iterating till convergence. And that will kind of keep things from bouncing around later on. And I found that to help with convergence, while still getting kind of something that's roughly in the shape of the ergodic distribution, which is highly efficient. I've also found that it can be helpful to draw training inputs from what's called a typical set, rather than a straight ergodic distribution. And what do I mean by that? A typical set is an information theoretic concept. And it sort of means that you're getting something that's kind of dispersed or representative of the distribution. All right, so this is going to help kind of fill the space more efficiently. All right. So what do I mean by that? I want to talk just for a minute or two about typical sets, because actually I found it to be very helpful. So what is a typical set? It's a set of draws from a distribution. So I have a distribution. It could be continuous, discrete, doesn't matter. I have some distribution, and I draw, say, 10 points from it. So maybe I have a standard normal, and I'm going to draw 10 points from it. A typical set is something that kind of matches the distribution in some sense, right? And that's what it means by typical, right? So the realized draws from the distribution share some features with the actual distribution itself. Now, importantly, this is going to mean that, right, it's not, typical sets are not going to be, say, the most likely sequence, because the most likely sequence doesn't really match the underlying distribution that much. For instance, the most likely sequence is just going to be a bunch of realizations of the mode of the distribution, which that's not really what you would kind of see typically from a realization of that, a draw from that. But even though it is the most likely thing to happen, right? So you define a typical set for a level of typicality epsilon. So epsilon is usually a pretty small number, and the typicality is basically 1 minus epsilon. And you can define the collection of typical sets as a subset of, if you have n different draws, it'll be a subset of the possible draws you can take given this epsilon. And to give you just a basic idea of what that looks like, here I have a standard normal distribution, and I'm drawing 10 things from it. I'm taking 10 draws from it, right? Here's a set that's atypical, but it's very likely. So this is a set which has high likelihood because it's very, very, the PDF is very high for all the realizations from this particular draw. In fact, how I derived this, I basically just took 10,000 different draws of 10, and I found the one with the highest likelihood, right? So I drew a whole bunch of times, and I found one with a very high likelihood. But it's not really telling you much. These draws are not telling you much about the underlying distribution itself, right? So a typical set would be something more like this, right? So this is a 0.1% typical set. This particular set of draws is in the 0.1% typical set. So it fleshes out the distribution a little bit more fully than this one does, even though it's actually a lot less likely than that previous distribution, right? So what we want to do is, you can see we could fill what we'd like to do is we actually want to draw typical draws from the ergodic set, not just the most likely draws, right? Or you're going to be more likely to kind of fill up the ergodic distribution if you're using typical draws, right? So how do you actually define a typical set? What you basically want is you basically want some notion of the average entropy, if you will, of the draws to match the actual entropy of the distribution. So the entropy of the distribution is given by H. And what that actually is it's the average of the log of the probabilities. That's just how you define entropy, and it's negative. So don't worry about very much what it is now. I'm not going to talk about it now. But it's a concept that's frequently used in information theory. And you basically are going to take the average of the log of the probabilities of your draws, and you want the average of that log to be close to the entropy of the actual distribution. That's all a typical set is. And if it's close enough, the smaller epsilon is, the closer you're demanding that they be. Right, so if epsilon is very, very small, then the level of typicality is going to be higher and higher and higher, right? Right. So I want to show you an example here with the Ariano model. This is a sovereign default model. This is the one I got really excited about when I was able to solve this pretty well. It's kind of like the consumption saving model. You have an output that follows an AR1 process. You have some debt that you pay off every single period. These are just short-term bonds. And then you have new bonds that you issue every single period. And the bond price is Q. That's this bond price function. It can depend on states today as well as new levels of issuance. And then tomorrow you have the option to default. So this is limited commitment model. You can't promise to repay new bonds that you've issued. Tomorrow, if it's in your best interest to default on that debt, you're going to default on that debt. If it's in your best interest to repay that debt, you'll repay that debt. Right? What do you get when you default? You don't have to pay your debt. Your debt is wiped clean, but you face some default costs. Why default? Right? And then with some probability, you re-enter credit markets with zero debt. And that probability is pi. And the bond price function is just given by the expected repayment probability. So it's the probability that tomorrow's tomorrow's repayment value is going to be higher than tomorrow's default value, divided by the lenders have access to some risk-free rate, and they're risk neutral. So that gives you this condition. It's just these three equations, the Ariano model. It's a very simple model. but it doesn't behave very nicely for a lot of standard techniques. But I found that machine learning does a wonderful job solving it, which is pretty cool. So I have that here. I'm going to go ahead and just start it running, just so that it's running. But here I do the same thing that I just described. So I'm going to use all of her parameters, Christina Ariano's parameters. So these are all her parameters. She has some notion of the risk-free rate, some notion of the sovereign's discount factor, CRRA utility. This is the volatility of the shock in the process. This basically governs the default cost. Here's a default cost function. This is the probability of reentry. I'm actually going to allow for recovery to debt here, but I'm going to set it close to 0. She doesn't have debt recovery here, but that basically allows me to use every single, that way I can train different functions, and they can all, because normally the default value doesn't depend on the level of debt. But it's actually easier for me with machine learning to have every function depend on every state. So I want the default value to depend a little bit on the level of debt because it'll work better for machine learning. So I'm just going to set a very small recovery rate on debt, and that's just going to do that for me. Two-dimensional problem, output and debt. Output varying from 3 standard deviations below to 3 standard deviations above. Debt varies from 0 to about 0.3. This guy's much more impatient than the risk-free rate, so he's always borrowing, so you don't really need to worry about him ever saving. Inputs, again, this is all the same machine learning stuff. Nothing's really changing. I have Gaussian quadratures to take expectations. Everything else is going to look basically the same. The only difference here is I'm actually going to train 3 different functions. I'm not just going to have a value function that I'm going to fit with machine learning. I'm going to have a repayment function. I'm going to have a default function, because those are actually 2 different equilibrium objects. I have a value function and default function, and they're all together. And then I have a policy function. I'm actually going to train the policy function B prime separately. That's going to allow me to simulate, because if I have the policy function, I can simulate it forward, right? So I have some policy function. So I'm training all of these things separately. I assume mean 0 on all of these. This default function is basically whenever default is bigger than repayment. And then I have a little function. Before I actually do the VFI, I'm going to write up a little length of code that simulates the model, that says, give me the current policy function and the current default function and run it forward for, I don't know, 10,000 periods, whatever it might be. This just simulates that, you know, simulates an AR1 for the output, simulates the law of motion given the debt issuance. You're going to have some default in there. You're going to have debt levels going all over. Save it all. Save that thing. That's all it's going to do. It's going to return basically a simulation. The output, the simulated output, and the simulated debt levels, right? And what I'm going to do, the rest of this is going to look exactly like we saw before. The only difference here is my scale mat here. This is where I draw. I'm actually going to draw it from an ergodic distribution. I'm going to build up an ergodic distribution over debt levels and output levels. I'm going to build up a 50 by 50 histogram of debt and output. I'm going to solve the model. At each iteration, I'm going to simulate the thing. Going to simulate that thing out, get an ergodic distribution, and I'm going to draw from that when I do my drawing, right? So here, I'm going to, the first thing I'm going to do, I'm going to, not only am I going to draw from it, I'm actually going to draw a typical set from the ergodic distribution. So I have an ergodic distribution that I've built up from previous iterations. And when I do a new draw, what I'm going to do is I'm going to check the entropy of that new draw, and I'm going to make sure it's close enough to the entropy of the actual ergodic distribution. So I'm actually looking to make sure I have a typical set. And if it's not a typical set, I'll just draw a new one. I'll just keep drawing until I get a typical set, because it's very cheap to draw. It doesn't take any time to draw from the distribution. It's no problem at all. So it doesn't slow anything down. I'm just going to make sure that I have a typical set. And then I just evaluate the Bellman then, right? I have Y today and B today. The first thing I'm going to do, I'm going to train the value of repayment, just a simple Bellman update. The value of default is an even easier Bellman update. I just take some expectations. When I do the value of repayment, I'm going to train not only the value of repayment, but also the policy function, so I can use it for simulations. And then the value of default. So I basically have a trained repayment, a trained default, a trained policy. I keep track of how much time it takes. So that takes about 2.3 seconds here to do that maximization and all that stuff. It takes about a second to update everything. I'm solving it 12 times. So when I actually train them now, I'm doing my convergence here, checking for convergence. And then I'm actually training 3 different Gaussian processes. I have a Gaussian process for inputs. I have a Gaussian process for repayment, for default, and for the policy function. And I'm going to optimize all of them several times. And it's just going to run until it's done. And it's actually going to converge pretty well. it's actually kind of neat because this thing is actually not actually a contraction error. You can't actually prove the distinct convergence, but we kind of know in this case it should converge, and it actually does if it's continuous. So I'm going to let that run for a while because we kind of know what the rest of it's going to look like. But I will show you basically what comes out of this is the following. So if you solve the model and run it to convergence and use what I just described, if I use a typical set of training inputs, let's say a 0.1% level of typicality, this is the ergodic distribution. So here's det ranging from 0 to 0.3. Here's output ranging from about 0.8 to about 1.2. You can see this has a very tight ergodic set relative to everything it could be. The ergodic distribution here is very concentrated, but it's also very nonlinear. It's very irregular, right? So when you're allowed to borrow a lot when your income is high, right? So you can borrow quite a bit. So the debt is tightly correlated with income and they both rise together, right? But you de-lever a lot when output is really low because the creditors basically won't let you borrow because they know you're going to default. So there's a lot of mass concentrated down here. And then as you increase debt, you get this correlation. So this is something I was puzzling over for years before I learned this. This is basically one of the reasons why a lot of other methods didn't work for sovereign default models, I think. So a lot of Chebyshev polynomial methods, for instance, basically rely on you building up a nice sparse grid over a region like this. But you have to build up the grid to correspond with the Chebyshev polynomials, not with the underlying problem itself. So the Chebyshev polynomials are going to put a lot of mass right here. They're going to put a lot of mass down here and down here. They're basically going to pick grid points that are nowhere near the ergodic distribution for a problem like this. And so then you go simulate the model, and basically every single policy function you're using is very far away. The whole ergodic distribution is very far away from all the points that you've chosen to approximate it. And so I've never found it to work in the past. But it works here because you can basically tailor your approximation to the region of interest. So yeah, so that worked very well, I found. I was very excited when I got this to work. And this is basically what's going to come out. So I can see what's probably getting close to being done here soon. It'll take a little bit longer. It's not going to be quite contractionary here because the contraction mapping theorem doesn't actually hold here, but you'll see eventually it will grind down. And it's just going to give us some nice things, and this is going to come out of it too. Okay, a few more minutes left here. Right. The only other thing I wanted to mention, really, in the paper, so I might recommend you just go look at the paper, the Scheide-Grabilionis paper, if you want kind of more on this, since we're running low on time. But it's kind of clear in the paper that they're trying to beat Smolyak. So they make a big deal about being able to handle more than 20 dimensions. They basically argue that Gaussian process regressions can't handle more than 20 dimensions that well, but that there's a way to use what they call active subspaces to do so. And what you basically do is you basically find some linear combination of your states in the higher than order dimensions, and you map them into a lower order dimension, and then you apply the Gaussian process regression. That's all that is. So you basically have, say, if cap D is your dimensionality, maybe it's 200 or something, maybe you have a 200-dimensional problem. And little d is something maybe less than 20, maybe 15 or 16 dimensions. You're basically going to find a function that you're going to map linearly your high state space into a smaller state space. And then you're going to apply Gaussian process regression on the smaller state space. And they call this active subspace. And so the magic is all in how do you find this W matrix. And so they give you a procedure to find it in the paper. But you're basically going to kind of do a uniform grid over the state space. You're going to kind of take some gradients, and you're going to do sort of a Jordan decomposition of the gradient, of the product of the gradients that you find, and then that's going to give you this weighting matrix, right? So I don't want to put too much stock into this because you can go read the paper to do it. Most of you probably aren't going to be doing this, so I don't want to spend too much time on this. But you can kind of handle it, and it basically is going to take kind of 500 dimensions or whatever it is and map it into, use linear techniques to shove it into 15 dimensions that are the most important, which is going to be some linear combination of all 500 of those dimensions, but map it into a smaller subspace, and then apply the Gaussian process on that subspace. Essentially what you're doing there. And so doing that, you can handle very, very large problems, they argue. They solve a problem with 500 continuous states in their paper without using a whole lot to do it. And it's also, for those of you who know a little bit about parallelization, we're going to talk about it next week in this course, but it's very easy to parallelize because it's just like a straight VFI. VFI is very easy to parallelize. So it's very easy to scale this thing up and make it actually very powerful. even more so than I'm doing on my desktop here. You could easily send this to a supercomputer with 500 cores and split it across all 500 cores and be done in seconds, right? So it's quite powerful. You might not use this that often for more than 20, unless you're more empirically minded. So maybe if you're thinking about doing some sort of reduced form regression using these techniques, you might have a lot more dimensions than 20 in that case, in which case this might be relevant for you. But you could also use this in the following way. Here's the really interesting thing about machine learning is it's actually so easy to scale up dimensions. So things that are totally counterintuitive to us actually become really feasible. And so here's an example. Suppose you're like a macro person and you want to calibrate some parameters to match the moments in the data, right? How do you normally do that? Well, you normally kind of fix the parameters, solve the model, see what they imply for empirical moments, and then update your kind of guess, and then do that again, and just keep doing it again and again and again. What you can actually do here is, because it's so easy to add dimensions, what you can actually do is if you have parameters you want to choose, you can actually add those parameters as dimensions and have them vary along a certain interval, and just set them as having a constant law of motion so that they'll never change. Given a fixed value, they'll never change. And you can do that for all your parameters. So maybe you have a 5-dimensional model, maybe you have 10 parameters you want to match. You can make it a 15-dimensional problem. And the cool thing about this is you solve it once. It's a 15-dimensional problem, you solve it once. But then you can just select the parameters as you want them, and then the model automatically adapts to the new parameters because you've solved it. So you only need to solve, you could calibrate potentially, especially if you use the active subspace, you could potentially calibrate dozens of parameters just solving the model once. You don't need to resolve the model. If you want to see what new parameters imply for the model, if you want to change the level of risk aversion or the discount factor, whatever it is, you just change that and it will tell you what the model does. You don't need to resolve the model again. And so that's sort of something that you would never really think of doing, because the curse of dimensionality would normally, I mean, you could do that with old techniques too, but the curse of dimensionality would be so horrible that it would never behoove you to do that. But here you can add states just as easily as you can add anything else. And so adding a whole bunch of states might mean that, you could do that. You could easily calibrate or estimate 10 different parameters, only ever solving the model once. Which is something that's which I think is quite cool, which is something that you can use this for. Neural networks, I don't know if I have a whole lot of time to talk about neural networks. It's already coming up on about noon. You can go over these slides and see what they look like, how you basically do them. They're really kind of a type of projection method in a certain sense, but it's basically highly nonlinear. So projection methods have Chebyshev polynomials and Legendre polynomials, all these other types of projection methods have a lot of linearity that are introduced into them, but that kind of make them work that allow us to understand them really well. Neural networks kind of have a similar flavor, but everything is nonlinear. So it's basically kind of nonlinear functions of nonlinear functions of nonlinear functions, and you kind of have layers and layers of nonlinear functions. So you have no idea what sorts of function spaces these span. You have no idea how any of this stuff really works, but apparently it works very well, right? So essentially you kind of have layers and layers of what are like basis functions, which are kind of like, they call them neurons or nodes. And they're basically simple little one-dimensional basis functions. Very simple, usually like an inverse tangent function or like a kinked linear function or something. But you have a whole mess of these, bunch of them. And then every input basically gets mapped into some of these simple basis functions. And then these simple basis functions aggregate things up and send them to another layer of basis functions. And these are called layers in a neural net. And then these aggregate up and send it to another layer. You can have a whole bunch of layers in there. And you can capture all sorts of crazy nonlinearities this way, in a way that can be very difficult to understand, but in a way that's not in principle difficult to do. Each neuron node is a simple little function. Like a common one is I think this is the ReLU, that's like rectified linear unit. And that's just 0 if x is less than 0 and x if x is bigger than 0. Sigmoid, it's like an exponential type function, and you have inverse tangent function. There's a whole bunch of different node functions you can use in a neural network. And essentially each one of these nodes gets a coefficient. There's a vector of coefficients in a layer L, and there's a vector of coefficients assigned to each node. So they're basically all the different dimensions are going to be sent to a bunch of these different nodes. And then basically some of these are going to, if you set the node to 0, if the coefficient is 0, you basically sever the connection to that node. And if the coefficient is big, then you're increasing the effect of that node. So you can kind of scale up and down these nonlinear responses. So you kind of start from some input points, you send them all to a bunch of these nodes. Some of them get severed, some of them blow up quite a bit, and then that's sent to another layer of node, which does the same thing. So you kind of get nonlinear functions inside of nonlinear functions inside of nonlinear functions. So it's very confusing to understand what's actually going on. But apparently it works very well. And all you have to do is basically find these coefficients, which is just like Chebyshev method. You just got to find the coefficients. And so essentially, usually what they do when they're training neural networks is they usually just use gradient-based methods. They usually just use some sort of BFGS algorithm or some sort of quadratic, approximately quadratic solver to solve these, to estimate these coefficients. And the estimation of those coefficients, they call it training. So this is going to feel a lot more like the implementation of projection methods than it would like the BFI. People use them too. A lot of people have been using neural networks in empirical work. Like I said, Jesus has used these to solve heterogeneous agents models. He basically used neural networks to do that. And that's the basic idea, except where in projection methods, you would have sort of a linear one-shot approximation to this thing using basis functions. Basically, neural networks are nonlinear and iterated combinations of simple basis functions as opposed to simple linear combinations of orthogonal basis functions. But you're basically using a black box solver over the coefficients, and you're just, every time you get new inputs, you just add more, you refine your coefficients. This is basically what Google's doing. Google Maps all operates on a big neural network, and it's basically just a huge vector of very carefully estimated coefficients in one of these neural networks. And what they'll actually do is whenever they introduce new, this is something I talked to my brother-in-law about, so I'll end on this story. It's kind of interesting. But I was talking to my brother-in-law about this, and he has a bunch of employees in Turkey. They have a lot of contractors out there that they have developed software for their business. He was out there taking a look at some of their facilities that they have over there and showing them around Turkey. And Google actually, Turkey built, I don't remember what it was, but there were some Olympic Games, I think, in Turkey at one point. And they built a huge stadium that they only used for the Olympics, and then they never used it again, really. What Google actually did was they rent out the stadium. And every time they use like Google Maps, whenever they come out with a new update to Google Maps or some of their other software, what they'll actually do is they'll hire like 500 people. They'll set up tables in this stadium and a bunch of computers, and they'll just hire a bunch of random people to, if it's maps, like something on Google Maps, then they'll actually like make sure that the directions are correct. So they'll see what Google's trying to do some new regions on the maps, and they'll basically cross-verify that the directions that Google Maps is giving it is correct. And then they feed it to the algorithm, and that trains the neural network. They update the coefficients to this. And so what they do is they have like 1,000 people sitting in this stadium clicking buttons to update the maps by hand for like a couple of weeks. And then they release it to the general population like 5% at a time. And every time they do this, every time the thing works, they update it positively. And so they basically slowly update the coefficients of this neural net doing this sort of thing. And that's basically how they train a lot of their big algorithms is using this sort of technique. But it's not in principle a difficult technique to understand. It's not in principle a difficult technique to implement. At the end of the day, you just wind up with a huge vector of coefficients that you can layer into, so the actual relationships between them are completely esoteric, but they work very well. So at any rate, that I think is going to do it for today. Does anybody have any questions on anything before we wrap things up here? No? Okay, very good. Well, I will take this. I'm going to, I've been recording this the whole time. So I'm going to post this somewhere where it'll be easy for the whole department to access. I'll try to find the best way to do it. But we'll stop recording here. And thank you all for joining us. And hopefully you all find this useful. So take care. And for those who are in my class, I will see you all next week then.
All right. Thank you very much.
Very good.